ये है सेमीकंडक्टर इलेक्ट्रॉनिक्स मटेरियल डिवाइस एंड द सिंपल सर्किट। तो पहले इसमें हम देखेंगे इसका कुछ पीवाईक्यू देख लेते हैं और फिर इसका देखेंगे एनसीईआरटी। तो पीवाईक्यू में है जिसमें जो है क्वेश्चन पूछा था कि द इलेक्ट्रॉन concentration in an n-type semiconductor is the same as the hole concentration in a p-type semiconductor. An external field electric is applied across each of them to compare the current in them. तो इसमें आ जाएगा कि given the electron concentration in the n-type semiconductor is equal to the hole concentration in the p-type semiconductor. When the electric field is applied across the semiconductor, the electron and the holes will move opposite to each other. The mobility of the n-type semiconductor is greater than the mobility of the p-type semiconductor. So the current in the n-type semiconductor is greater than the current in the p-type semiconductor. The answer है ऑप्शन सी कि current in the n-type is greater than current in the p-type. नेक्स्ट आता है कंसिडर द फॉलोइंग स्टेटमेंट ए एंड बी एंड आइडेंटिफाई द करेक्ट स्टेटमेंट। तो ए जो है जेनर डायोड इज कनेक्टेड इन द रिवर्स बायस व्हेन यूज्ड एज ए वोल्टेज रेगुलेटर, सही बात है। द पोटेंशियल बॉडी ऑफ पी एन जंक्शन लाइज बिटवीन द 0.1 to 0.3 वोल्ट, तो दोनों सही है। तो इसका आंसर क्या आ जाएगा कि एज करेक्ट बट पी इज है जो इनकरेक्ट होगा कि क्योंकि जनरल डायोड ये टाइप ऑफ द स्पेशल पी एन जंक्शन डायोड दैट ऑपरेट्स इन द रिवर्स बायस, thus it is used a voltage regulator, so the statement is correct. लेकिन the potential value of the PN junction for the silicon is 0.67, 0.6 से 0.1 and for germanium is 0.2 से 0.35, so the statement B जो क्या हो जाएगा इनकरेक्ट हो जाएगा। तो ये है जो पोटेंशियल वैल्यू ऑफ PN जंक्शन लाइज बिटवीन, अब इसमें यहाँ पर लिखा नहीं है 0.1 to 0.3, तो यह है जो अच्छा क्वेश्चन था इसमें, क्योंकि 0.6 जो होता है सिलिकॉन का 0.6 से 0.1 होता है और जर्मेनियम का 0.2 से 0.35 होता है। तो इसमें जो है 0.2 से 0.35 होता है, तो इसमें जो है 0.1 तो किसी का है ही नहीं है, तो ये स्टेटमेंट गलत हो जाएगा। तो ये है जो अच्छा क्वेश्चन है पूछ दिया था। नेक्स्ट है कि द आउट ऑफ द फ्लोइंग विच वन इज ए फॉरवर्ड बायस डायोड। तो ये पी एन जंक्शन इसमें जो हो गया 2, इधर -4 -2, तो ये हो गया इधर हाई होना चाहिए इधर लो होना चाहिए, इधर 0 -3, तो आंसर आएगा ऑप्शन डी कि a PN junction diode is forward bias when the P side connected with more positive potential than the N side. Hence the option D diode circuit है जो क्या है तो forward biased है। फिर आता है कि intrinsic semiconductor is converted into N-type intrinsic semiconductor by doping it with the, आंसर आएगा ऑप्शन ए phosphorus. When the pentavalent phosphorus impurity is doped with the intrinsic semiconductor germanium और silicon, तो N-type semiconductor है जो फॉर्म होता है। अगला क्वेश्चन है कि द इंक्रीज इन द विथ ऑफ द डिप्लीशन रीजन ऑफ ए पी एन जंक्शन डायोड ड्यू टू, तो आंसर आएगा ऑप्शन ए रिवर्स बायस ओनली। तो अंडर द रिवर्स बायस कंडीशन द होल्स ऑफ द पी साइड अट्रैक्टेड टुवर्ड्स द नेगेटिव टर्मिनल ऑफ द बैटरी एंड द इलेक्ट्रॉन्स ऑफ द एन साइड अट्रैक्टेड टुवर्ड्स द पॉजिटिव टर्मिनल ऑफ द बैटरी। This increase the bit layer of the depletion layer. However, in the case of the forward biasing, the bit of the depletion layer decreases. Hence, the correct option क्या आ जाएगा ए हो जाएगा। नेक्स्ट है कि the solid which have the negative temperature coefficient of the resistance, आंसर आएगा ऑप्शन सी इंसुलेटर एंड सेमीकंडक्टर का है जो नेगेटिव होता है। इंसुलेटर एंड सेमीकंडक्टर आर दोज सॉलिड which have the negative temperature coefficient of the resistance as when the temperature increases number of the free electrons increase in both insulator and the semiconductor, तो आंसर आएगा ऑप्शन सी। अगला है कि an LED is constructed from a PN junction diode using the GaAsP, the energy gap is 1.5 इलेक्ट्रॉन वोल्ट, तो वेवलेंथ ऑफ द लाइट इमिटेड बिल कितना हो जाएगा, तो इसमें है कि the energy of the light of the wavelength lambda is given by E equal to h nu यानी कि h by lambda, तो lambda is equal to h by e। h जो है प्लैंक कांस्टेंट है 6.63 × 10⁻⁴ जूल सेकंड। c स्पीड ऑफ लाइट है 3 × 10⁸ मीटर पर सेकंड। e जो एनर्जी गैप है 1.9 यानी 1.9 × 1.6 × 10⁻⁹ जूल, तो लैम्डा हो जाएगा 6.63 × 10⁻⁴ 3 × 10⁸ by 1.19 × 1.6 × 10⁻⁹ यानी 6.5 × 10⁻⁷, तो 654 नैनोमीटर। द वेवलेंथ ऑफ द लाइट इमिटेड फ्रॉम द एलईडी कितना हो जाएगा 654 नैनोमीटर, तो इसका आंसर आएगा ऑप्शन बी 654 नैनोमीटर। देखो एंगस्ट्रॉम में भी दिया हुआ है लेकिन आंसर आएगा 654 नैनोमीटर। नेक्स्ट है कि फॉर ए पी टाइप सेमीकंडक्टर विच ऑफ द फॉलोइंग स्टेटमेंट इज ट्रू, आंसर है कि होल्स आर द मेजॉरिटी कैरियर्स एंड द ट्राइवेलेंट एटम्स आर द डोपेंट्स। तो पी टाइप सेमीकंडक्टर आर ऑब्टेन्ड बाय द ट्राइवेलेंट इम्प्योरिटी, example boron, aluminum, gallium or indium is added to the intrinsic semiconductor, example germanium or silicon. In other words, the dopant in the p-type semiconductor is a trivalent atom. Thus, this addition creates deficiency of the valence electron, which are most commonly known as the holes. These are the majority charge carriers in this type of the semiconductor. However, in the n-type semiconductor, the dopant for pentavalent impurity also the majority charge carrier for the electrons. फिर आता है In the PN junction diode, change in the temperature due to the heating, the answer option D, affects the overall VI characteristic of the PN junction. So due to the increase in the temperature because of the heating, thermal collision between the electrons and the holes increases, thus the net electron hole pair increases. This leads to the increase in the current in the diode and the overall resistance of the diode changes. This in turn change both the forward biasing and the reverse biasing, thus the overall VI characteristic of the PN junction diode gets affected. Next, which of the following represents the forward bias diode? The answer option A is 0 volt and the -2 volt. In the forward biasing of a PN junction, P side of the junction diode is connected to the higher potential and N side of the junction is connected to the lower potential. So ऑप्शन ए है जो करेक्ट आंसर जाएगा. अगला क्वेश्चन, कंसिडर द जंक्शन डायोड एज आइडियल. द वैल्यू ऑफ द करंट फ्लोइंग थ्रू ए और बी कितना हो जाएगा? तो लेट अस अज्यूम द करंट फ्लोइंग थ्रू द डायोड आई फ्रॉम द कंडीशन आई इक्वल टू वी माइनस वी इक्वल टू आर. तो 4 माइनस माइनस 6 इक्वल टू 1 किलो ओम. तो 10 पर 1 गुना 10 पर माइनस 3 इक्वल टू 10 पर माइनस 2. तो आंसर इसको कितना आएगा? 10 पर माइनस 2 एम्पियर. फिर आता है द गिवन सर्किट हैज टू आइडियल डायोड्स कनेक्टेड एज शोन इन द फिगर. द करंट फ्लोइंग थ्रू द रेसिस्टर R1 है जो कितना हो जाएगा? तो इसका आ जाएगा आंसर ए कि वी नो दैट डायोड ओनली कंडक्ट्स इन द फॉरवर्ड बायस कंडीशन. इन द गिवन सर्किट डायोड D1 will be in the reverse bias, so it will block the current, and diode D2 it will be in the forward bias, it will pass the current. तो I is equal to V by R1 plus R2 यानी कि 10 by 2 plus 2 यानी कि 2.5 एम्पियर. इसका आंसर कितना जाएगा? ऑप्शन जाएगा, इसका आंसर कितना जाएगा? तो 2.5 एम्पियर ऑप्शन ए जाएगा. फिर आता है कि if in a PN junction a square input signal of the 10 volt is applied as shown, तो as it is forward bias so it takes the positive value, hence the option D is correct value. आंसर आएगा ऑप्शन डी 5 वोल्ट यह हो जाएगा. नेक्स्ट आता है कि इन द गिवन फिगर ए डायोड डी कनेक्टेड टू द एक्सटर्नल रेजिस्टेंस ऑफ आर इक्वल टू 4 ओम एंड EMF ऑफ 3.5 वोल्ट. इफ द बैरियर पोटेंशियल ऑफ डेवलप्ड अक्रॉस द डायोड इज 0.5 वोल्ट, इन द करंट इन द सर्किट कितना हो जाएगा? तो आंसर आएगा ऑप्शन है 30 मिली एम्पियर. क्योंकि गिवन एक्सटर्नल रेजिस्टेंस आर इक्वल टू 4 ओम और EMF इज 3.5 वोल्ट. तो अगर यहाँ से देखें तो पोटेंशियल बैरियर अक्रॉस द डायोड हो जाएगा 0.5 वोल्ट. पोटेंशियल डिफरेंस ऑन आर इक्वल टू 3.5 माइनस वोल्ट माइनस 0.5 वोल्ट यानी कि 3.0 वोल्ट. तो गिवन करंट इन द सर्किट हो जाएगा आई इक्वल टू V/R यानी कि 3/4 यानी कि 0.03 एम्पियर यानी कि 30 मिली एम्पियर. आंसर चल जाएगा 30 मिली एम्पियर ऑप्शन ए. नेक्स्ट है द गिवन ग्राफ रिप्रेजेंट द VI कैरेक्टरिस्टिक ऑफ अ सेमीकंडक्टर डिवाइस, व्हिच ऑफ द फॉलोइंग स्टेटमेंट इज करेक्ट? तो it is a VI characteristic for the solar cell where point A represent the open circuit voltage and the point B represent the short circuit current. तो पहला है जो सही है. दूसरा it is for a solar cell and point C and B represents open circuit voltage and the current respectively, तो ये गलत हो जाएगा. फिर आता है it is for a photodiode and point C and B represent open circuit voltage and the current respectively, ये भी गलत हो जाएगा. it is for LED and point A and B represent open circuit voltage and the short circuit current respectively, तो ये भी गलत हो जाएगा. अब आगे है कि the barrier potential of a PN junction depends upon the, तो ये डिपेंड करता है किस पर. एक तो डिपेंड टाइप ऑफ सेमीकंडक्टर मटेरियल पर, अमाउंट ऑफ डोपिंग पर, और तीसरा है टेम्परेचर पर. तीनों पर. तो ऑप्शन 1, 2 एंड 3. बैरियर पोटेंशियल डिपेंड्स ऑन ऑल 3 ऑप्शन. बैरियर पोटेंशियल डिपेंड्स ऑन दी मटेरियल यूज्ड टू मेक द PN junction diode, whether it is silicon or germanium. It also depends on the amount of the doping due to which the number of the magnetic carriers will change. It also depends on the temperature due to which the number of the magnetic carriers will change. फिर आता है in the N-type semiconductor, which of the following statement is true? The holes are magnetic carriers and the pentavalent atoms are the dopants. So in the N-type semiconductors can be produced by doping an impurity atom of the valence of 5. That means pentavalent atoms, phosphorus, holes are magnetic carriers in them. अगला सवाल कि C and Fi both have the same lattice structure having 4 bonding electrons in each. Having C is insulator whereas Fi is intrinsic semiconductor. This is because the 4 bonding electrons in the case of the C lie in the second orbit, whereas in the case of the Fi they lie in the third. The 4 bonding electrons in the case of the C lie in the second orbit, whereas in the case of the Fi they lie in the third orbit. So the loosely bonded valence electrons are present in the Fi as compared to the C. Next है, if a small amount of the antimony is added to the germanium crystal, तो when a small amount of antimony is added to germanium crystal, the crystal becomes N-type semiconductor because antimony is a pentavalent substrate. तो आंसर है ऑप्शन बी कि there will be more free electrons than the holes in the semiconductor. फिर आता है कि in the forward biasing of the PN junction, ऑप्शन सी सही होगा. The positive terminal of the battery connected to a P side and the depletion region becomes thin. तो in the forward biasing of the PN junction, the positive terminal of the battery connected to the P side and the depletion region becomes thin. अगला क्वेश्चन है कि which one of the following statement is false? तो the magnetic carriers in the N-type semiconductor are holes. The p-type semiconductor are obtained by the adding a small amount of the traveling impurity to a pure sample of the semiconductor. G. Moiety charge carriers holes moiety charge carrier electrons. N-type semiconductor obtained by the adding a small amount of pentavalent impurity to a pure sample of the semiconductor. G. Moiety charge carriers electrons. The resistance of the intrinsic semiconductor increases with the increase of the temperature. नेक्स्ट है कि सोडियम है द बॉडी सेंटर्ड पैकिंग ठीक है डिस्टेंस बिटवीन द टू नियरेस्ट एटम 3.7 एंगस्ट्रॉम. तो लैटिस पैरामीटर क्या हो जाएगा तो नेवर डिस्टेंस ऑफ द बॉडी सेंटर्ड क्यूब हो जाएगा क्यूब सेल डी इज इक्वल टू √3 ए वेयर ए इज द लैटिस पैरामीटर. तो 3.7 इक्वल टू हो जाएगा √3 a/2 यानी ए इक्वल टू हो जाएगा 2 इंटू 3.7/√3 यानी 4.3 एम्पियर. तो आंसर होगा ऑप्शन बी यानी 4.3 एम्पियर. फिर आता है कि इन ए पी-एन photodiode is fabricated from a semiconductor with a band gap of 2.5 electron volt. It can detect a signal of the wavelength. तो E इक्वल होता है h यानी कि hc by lambda. तो लैम्डा इक्वल होता है hc by e. Substituting the value of h यानी in the above equation लैम्डा हो जाएगा 6.6 × 10⁻⁻34 गुना 3 × 10⁻8 by 2.5 गुना 1.5 × 10⁻19 यानी 5 एंगस्ट्रॉम. तो 4 एंगस्ट्रॉम कम होता है 5 एंगस्ट्रॉम से. तो सिग्नल ऑफ द वेवलेंथ ऑफ 4 एंगस्ट्रॉम कैन बी डिटेक्टेड बाय द फोटोडायोड. तो आंसर होगा ऑप्शन डी 4000 एंगस्ट्रॉम. फिर आता है कि ये पी-एन फोटोडायोड इज मेड अप ऑफ मटेरियल विद अ बैंड गैप ऑफ 2 इलेक्ट्रॉन वोल्ट. द मिनिमम फ्रीक्वेंसी ऑफ द रेडिएशन दैट कैन बी ऑब्जर्व्ड बाय द मटेरियल कितना हो जाएगा तो लेट द एनर्जी ऑफ द रेडिएशन फॉलिंग ऑन द पी-एन फोटोडायोड बी इज इक्वल टू एच न्यू. द मिनिमम एनर्जी रिक्वायर्ड 2 इलेक्ट्रॉन वोल्ट. तो 2 इलेक्ट्रॉन वोल्ट इज इक्वल टू एच न्यू. तो न्यू इज इक्वल टू हो जाएगा 2 EV by h यानी 2 × 1.6 × 10⁻19 by 6.6 × 10⁻34 यानी 5 × 10⁻14 हर्ट्ज. आंसर इसका हो जाएगा 5 × 10⁻14 हर्ट्ज ऑप्शन बी. फिर आता है कि इफ द लैटिस पैरामीटर ऑफ ए क्रिस्टल स्ट्रक्चर इज 3.6 एम्पियर एंगस्ट्रॉम है देन द एटॉमिक रेडियस इन द एफएफसी क्रिस्टल कितना हो जाएगा तो फॉर द एफएफसी क्रिस्टल r इक्वल टू a/2 √2 वेयर r रेडियस ऑफ द एटम इन द पैकेजिंग है. a जो है एज लेंथ ऑफ द क्यूब है तो a इक्वल टू 3.6 एंगस्ट्रॉम. तो r इक्वल टू 3.6/2 × 1.4 यानी 1.27 एंगस्ट्रॉम. तो आंसर कितना जाएगा आंसर होगा ऑप्शन डी 1.27 एंगस्ट्रॉम. नेक्स्ट आता है कि फॉर ए क्यूबिकल क्रिस्टल स्ट्रक्चर विच वन ऑफ द फॉलोइंग रिलेशन इंडिकेटिंग द फुल स्ट्रक्चर इज करेक्ट. तो आंसर होगा ऑप्शन डी कि a इज इक्वल टू b इज इक्वल टू c और अल्फा इज इक्वल टू बीटा इज गामा इक्वल टू 90 डिग्री. तो इन क्यूबिकल क्रिस्टल द क्रिस्टल एक्सिस आर परपेंडिकुलर टू द वन अनदर. अल्फा इज इक्वल टू बीटा इज गामा इक्वल टू 90 डिग्री एंड द रिपीटेटिव इंटरवल इज द सेम अलोंग द 3 एक्सिस. a इज इक्वल टू b इज इक्वल टू c. फिर आता है कि इन द एनर्जी बैंड diagram of a material shown below the open mid circles and the filled circles denote holes and electrons respectively. तो material क्या होगा तो आंसर आएगा a p-type semiconductor. Since in the given diagram we see that there are more number of the holes so it is a p-type semiconductor. तो आंसर आएगा ऑप्शन a. नेक्स्ट है कि फॉरवर्ड बायस डायोड क्या होता है तो d हो जाएगा 0 वोल्ट और -2 वोल्ट. The p-n junction diode can be shown as if the p side of the p-n junction diode is given more positive potential or the positive terminal of the battery and n side is connected to a less potential or one terminal of the battery then it is forward bias. In the option D, p side is 0 volt and n side is -2 volt. So the p is at higher potential hence it is a forward bias. p-n junction diode is mainly used as a rectifier. फिर आता है कि कॉपर है द फेस सेंटेड क्यूबिक लैटिस एफसीसी लैटिस विद द इंटर एटॉमिक स्पेसिंग इक्वल टू 2.5 पर एंगस्ट्रॉम. द वैल्यू ऑफ द लैटिस कांस्टेंट फॉर दिस लैटिस कितना हो जाएगा तो हम जानते हैं कि इंटर एटॉमिक इस सब पहले पूछता था कि इंटर एटॉमिक स्पेसिंग फॉर द एफसीसी लैटिस इन बाय r इक्वल टू a/2 के स्क्वायर प्लस a/2 के स्क्वायर प्लस 0 के स्क्वायर a/√2 वेयर a being लैटिस कांस्टेंट. तो a इक्वल टू √2r यानी √2 गुना 2.54 यानी 3.59 एंगस्ट्रॉम. तो इसका आंसर कितना जाएगा 3.59 एंगस्ट्रॉम. पहले इसे पूछा था अब नहीं आएगा. नेक्स्ट है चूज ओनली फॉल्स स्टेटमेंट फ्रॉम द फॉलोइंग. तो इसमें आ जाता है कि द इन एन इन्सुलेटर एनर्जी गैप इज ऑड. इन्सुलेटर में कितना होता है इन इन्सुलेटर एनर्जी गैप इज ऑफ ऑर्डर ऑफ 5 to 10 इलेक्ट्रॉन वोल्ट एंड इट इज practically impossible to impart this much amount of energy to the electrons in valence band so to jump to the conduction band. तो आंसर ये है जो सही है. In the semiconductor, with a rise in the temperature, more electrons from the valence band jump to the conduction band, and this result in the increase in the conductivity. So choice B है जो भी सही है. In the conductor of the conduction band is either partially filled or the conduction band overlaps on the valence band. तो choice C भी correct है. In semiconductor, resistivity decreases with increase in temperature. तो choice D है जो wrong हो जाएगा. अगला क्वेश्चन है कि जेनर डायोड यूज फॉर तो इसका आ जाएगा स्टेबलाइजेशन के लिए यूज करते हैं. ऑप्शन सी आ जाएगा. जेनर डायोड इज सिलिकॉन क्रिस्टल डायोड हैविंग एन अनयूजुअल रिवर्स करंट कैरेक्टरिस्टिक व्हिच इज पार्टिकुलरली सुटेबल फॉर वोल्टेज रेगुलेटिंग पर्पस और द वोल्टेज स्टेबलाइजेशन पर्पस. फिर आता है एप्लीकेशंस ऑफ द फॉरवर्ड बायस टू पी-एन जंक्शन इज. तो आंसर आएगा ऑप्शन ए इंक्रीज द नंबर ऑफ द डोनर्स ऑन द एन साइड. तो on applying the forward bias to p-n junction diode, it increases the number of the donors on the n side and decrease the potential barrier. It also decrease the electric field of the depletion layer. फिर आता है of the diodes shown in the following diagram, which one is the reverse biased? तो इसका आंसर आएगा ऑप्शन सी, क्योंकि ये 0 है, इन प्लस है, तो ये है जो रिवर्स बायस आ जाएगा. नेक्स्ट है कि इन पीएन जंक्शन डायोड फोटो सेल द वैल्यू ऑफ द फोटो इलेक्ट्रोमोटिव फोर्स प्रोड्यूस्ड बाय द मोनोक्रोमैटिक लाइट इज प्रोपोर्शनल टू द बैरियर. इसका आंसर आएगा क्या? इसका आंसर आ जाएगा ऑप्शन बी कि द इंटेंसिटी ऑफ द लाइट फॉलिंग ऑन द सेल. तो इसमें आता है in the photoconductive cell, when the monochromatic light is incident on the transparent metallic film, a force produced called the photoelectromotive force stimulates the emissions of electric current, where the photovoltaic action creates a potential difference between the 2 points. The magnitude of this current depends upon the intensity of the incident light, hence the photoelectromotive force produced by the monochromatic light is proportional to the intensity of light falling on the cell. Next है कि the peak voltage in the output of a half wave diode rectifier fed with a sinusoidal signal without filter is 10 volt. The DC component of the output voltage कितना हो जाएगा? तो the output DC component of the half wave rectifier is V output equal to peak voltage by pi यानी 10 by pi. तो इसका आंसर होगा ऑप्शन बी 10 by pi volt. फिर आता है कि इन द सेमीकंडक्टर एट ए रूम टेम्परेचर, तो ऑप्शन ए सही होगा. द वैलेंस बैंड इज पार्शियली एम्प्टी एंड द कंडक्शन बैंड इज पार्शियली filled. Energy band film of a semiconductor is shown. In the semiconductor, valence band and the conductor bands are separated by an energy gap called the forbidden energy gap. It is very small. At room temperature, some electrons in the valence band acquire thermal energy. This energy is more than the forbidden energy gap Eg. Thus, they jump into the conduction band and leave their vacancy in the valence band, which act as a holes. Hence, at the room temperature, valence band is partially empty and the conduction band is partially filled. तो ये होता है कनेक्शन बैंड, ये होता है बैलेंस बैंड, और ये हो गया फॉरवर्डिंग एनर्जी गैप. Eg इक्वल टू कितना आता है? 1.1 इलेक्ट्रॉन वोल्ट. नेक्स्ट है कि द फुल वेव रेक्टिफायर सर्किट इज ऑपरेटिंग फ्रॉम 50 हर्ट्ज मीन्स द फंडामेंटल फ्रीक्वेंसी इन द रिपल कितना हो जाएगा? तो द फुल वेव रेक्टिफायर रिपल फ्रीक्वेंसी इज इक्वल टू 2 इंटू इनपुट फ्रीक्वेंसी यानी 2 इंटू 50 यानी आ जाएगा कितना? 4 हर्ट्ज. आंसर आएगा ऑप्शन बी 4 हर्ट्ज. फिर आता है कि बैरियर पोटेंशियल ऑफ ए पीएन जंक्शन डायोड डू नॉट डिपेंड अपॉन इट. आंसर आएगा सी, डायोड डीआईएन पर डिपेंड नहीं करता है. बैरियर पोटेंशियल डू नॉट डिपेंड अपॉन द डायोड डीआईएन बट इट डिपेंड्स ऑन द टेम्परेचर, doping intensity and the forward biasing. फिर आता है कि for a given circuit of the ideal PN junction diode, which of the following is correct. तो इसमें आएगा कि in the forward biasing the diode conducts for the ideal junction diode, the forward resistance is 0. Therefore, the entire applied voltage of the resistance R. While in the reverse biasing the diode by not conduct, so it has infinite resistance. Thus, the voltage across the R is 0 in the reverse biasing. The answer is option A कि in the forward biasing the voltage across R is V. अगला क्वेश्चन है कि फॉर कंडक्शन इन पी एन जंक्शन द बायसिंग इज. तो आंसर होगा ऑप्शन बी हाई पोटेंशियल ऑफ द पी साइड एंड लो पोटेंशियल ऑफ द एन साइड. फॉर द कंडक्शन ऑफ a p-n junction it should be forward bias because it offers minimum resistance to the flow of the current. For this, p side must be connected to a positive terminal higher potential and n side must be connected to a negative terminal lower potential. Figure below for the p-n junction in a connecting of state forward bias condition है दिखाया हुआ है. नेक्स्ट है कि नंबर ऑफ द एटम्स पर यूनिट सेल इन द बेसिस लैटिस कितना हो जाएगा? तो नंबर ऑफ एटम्स पर यूनिट सेल इज बाई एन इक्वल टू एन बी प्लस एन एफ बाई 2 प्लस एन सी बाई 8. पर एन बी जो है नंबर ऑफ एटम्स सेंटर्ड इन द बॉडी है, एन एफ जो है नंबर ऑफ एटम्स सेंटर्ड इन द फेस है, एन सी जो है नंबर ऑफ एटम्स सेंटर्ड एट द कॉर्नर है. तो द बेसिस स्ट्रक्चर एन बी इक्वल टू 1, एन एफ इक्वल टू 0, एन सी इक्वल टू 8. तो एन इक्वल टू 1 प्लस 0 बाई 2 प्लस 8 बाई 8 इक्वल टू कितना आ जाएगा? 2. तो आंसर आएगा ऑप्शन बी 2. फिर आता है कि इन द बेसिस स्ट्रक्चर ऑफ द लैटिस कांस्टेंट ए द मिनिमम डिस्टेंस बिटवीन द एटम कितना हो जाएगा? तो इन द बेसिस स्ट्रक्चर द पोजीशन वेक्टर ऑफ द नियरेस्ट नेबर्स ऑफ द ऑरिजिन आ जाएगा. प्लस माइनस ए बाई 2 आई कैप प्लस माइनस ए बाई 2 जे कैप प्लस माइनस ए बाई 2 के कैप. द डिस्टेंस बिटवीन एनी टू नियरेस्ट नेबर्स इज गिवन बट द रिजल्टेंट ऑफ देयर पोजीशन वेक्टर इज ए बाई 2 के स्क्वायर प्लस ए बाई 2 के स्क्वायर प्लस ए बाई 2 के स्क्वायर यानी रूट ओवर 3 ए स्क्वायर बाई 4 यानी रूट ओवर 3 बाई 2 ए. आंसर आएगा ऑप्शन ए रूट ओवर 3 बाई 2 ए. नेक्स्ट है इफ द इंटरनल रेजिस्टेंस ऑफ सेल इज नेग्लिजिबल देन द करंट फ्लोइंग थ्रू द सर्किट है जो कितना हो जाएगा? तो in the circuit diode D1 is forward bias and the diode D2 is reverse bias. Therefore, no current flow in the arm containing D2 and all of the current flow through the arm containing D1. So the current flowing through the circuit is given by I is equal to V by R equivalent यानी 5 by 20 प्लस 30 यानी 5 by 50 एम्पियर. R equivalent is equal to हो जाता है 20 प्लस 30 यानी कि तो आंसर होगा ऑप्शन क्या? 20 B 5 by 50 एम्पियर. अगला क्वेश्चन है कि सिलिकॉन एंड CU आर कूल्ड टू ए टेम्परेचर ऑफ 300 केल्विन देन द रेसिस्टिविटी क्या हो जाएगा? तो Resistivity of a metal is directly proportional to the temperature, because if temperature coefficient is positive and the resistivity of a semiconductor is inversely proportional to the temperature due to its negative temperature coefficient. This implies that with decrease in the temperature, resistivity of the metal decreases while that of the semiconductor increases. Here phi is a semiconductor and phi is a metal. So resistivity of the silicon increases but that of the phi क्या होता है decreases. आंसर आएगा ऑप्शन ए कि फॉर द सिलिकॉन इंक्रीजेज एंड फॉर द पी क्या हो जाएगा डिक्रीजेज. नेक्स्ट है इन बीच ऑफ द फ्लोइंग फिगर जंक्शन डायोड ई फॉरवर्ड बायस. आंसर आएगा ऑप्शन बी 0 वोल्ट माइनस 2 वोल्ट. तो फॉर द फॉरवर्ड बायस of a PN junction, P should be at higher potential than NFAD. Now we apply this rule to a P4 option. तो आंसर इसमें तो सिंपल है. नेक्स्ट है कि इन पी टाइप सेमीकंडक्टर द म्यूनिटी चार्ज के टाइप का होता है, तो इसमें आता है ए होल्स होता है. Semiconductor doped with the acceptor atoms are called the p-type semiconductor. The p stands for the positive to imply that the holes are introduced into the valence band, which behave like the positive charge carriers, greatly in number than the electrons in the conduction band. In a p-type semiconductor, holes are the magnetic carriers and electrons are the magnetic carriers. फिर आता है कि इन द फॉरवर्ड बाय ऑफ द width ऑफ द डिप्लीशन लेयर इन a p-n junction डायोड कितना हो जाएगा, तो आंसर ऑप्शन बी डिक्रीज हो जाता है. Since in the forward biasing, negative of the battery is connected to N side and the positive terminal of the battery connected to P side, hence an electric field is created in direction opposite to the E in the potential barrier region. Hence, डिप्लीशन रीजन ऑफ ए पीएन जंक्शन डायोड क्या होता है डिक्रीज हो जाता है. फिर आता है डिप्लीशन लेयर कंसिस्ट ऑफ, तो आंसर आएगा डी इमोबाइल आयंस होता है. जब when a piece of the p-type material is in contact with the n-type material, then to bring the Fermi levels in the line, electrons in the conduction band on the n-type side travels across the junction and leave the positively ionized impurity atoms unutilized. Consequently, there is a positive charge region adjacent to the junction of the n-type material. On the p-type side, the electrons which have transversed the boundary recombine with the positive holes in the valence band near to the junction of a p-type side. There is a layer of the unneutralized negatively ionized trivalent impurity which forms a negatively charged region. This region around the junction is called a charge depletion region or a space charge region. फिर आता है कि इन ए जंक्शन डायोड द होल्स आर ड्यू टू, आंसर आएगा ऑप्शन बी मिसिंग इलेक्ट्रॉन्स. इन ए जंक्शन डायोड व्हेन इलेक्ट्रॉन जंप्स थ्रू ए कंडक्शन बैंड देन फ्रॉम द वैलेंस बैंड ड्यू टू द थर्मल एगिटेशन और एनी अदर circumstances, then the vacancy created in valence band which has the positive charge equal to the charge of the electron in the magnitude. This is called the hole. The holes in the junction diode are due to the missing electrons. फिर आता है which of the following when added to an impurity in the silicon produces n-type semiconductor, तो आंसर आएगा ए phosphorus. When pentavalent impurity is added to the silicon, then the n-type semiconductor is formed. Out of a given option, only phosphorus is pentavalent, for it would be doped to the silicon to make it n-type semiconductor. फिर आता है कि semiconducting device is connected in a series in the circuit with a battery and a resistor. A current is allowed to pass through the circuit. If the polarity of the battery is reversed, the current drops to almost zero. The device may be. So we know that in the forward biasing of a PN junction, the current is of the order of the milliampere, while in the reverse biasing, the current is of the order of the microampere. The device क्या हो जाएगा, तो PN junction हो जाएगा. आंसर जाएगा ऑप्शन ए PN junction. फिर आता है द कॉज ऑफ द पोटेंशियल बैरियर इन अ PN डायोड कितना हो जाएगा, तो आंसर जाएगा ऑप्शन डी concentration of the positive and the negative charge near the junction, तो ऑप्शन जाएगा ऑप्शन डी. In a PN junction diode, magnetic carrier are holes on the p side and electrons on the n side. The holes diffuse on the n side and electrons to the p side. Diffusion causes a layer of the positive charge in the n region and layer of negative charge in the p region near the junction. This lower layer of the positive charge creates an electric field which exerts a force on the electrons and holes against their diffusion. This electric field becomes strong enough as diffusion proceeds to stop it. In the equilibrium position, there is a barrier for the charge motion with the n side at the higher potential than the p side. The junction region has a very low density of either p or n type carriers because of the interdiffusion. It is called as the depletion region. अगला सवाल है कि the diode used in the circuit shown in the figure has a constant voltage drop of the 0.5 volt at all current and the maximum power rating of 4 milliwatt. What should be the value of the resistor I connected in a series with the diode for obtaining the maximum current I? तो करंट इन द सर्किट आई इक्वल टू पी बाई वी डी यानी 100 गुना 10 माइनस 10 बाई 0.5. वी डी जो है वोल्टेज ड्रॉप एक ऑफ द डायोड है 200 गुना 10 के पावर माइनस 10 एम्पियर. तो वोल्टेज क्रॉस रेसिस्टेंट आर इक्वल टू वी डफ इक्वल टू 1.5 माइनस 0.5 यानी कि 1 वोल्ट और रेसिस्टेंट आर इक्वल टू वी डफ बाई आई यानी 1 बाई 200 गुना 10 माइनस 10, तो कितना आ जाएगा 5 ओम. तो इसका आंसर कितना आ जाएगा ऑप्शन सी 5 ओम. नेक्स्ट है टू ऑब्टेन पी टाइप जर्मेनियम सेमीकंडक्टर इट मस्ट बी डोपेड विद दी, तो आंसर आएगा ऑप्शन बी इंडियम के साथ है जो डॉप करना चाहिए. if a travelent impurity mixed in a pure intrinsic semiconductor, then it becomes a p-type semiconductor. As given, indium is travelent impurity, so it must be doped to the G or Fi to make it p-type semiconductor. फिर आता है कि when arsenic is added to as an impurity to the silicon, the resulting material is, when a small amount of pentavalent impurity added to the pure semiconductor, it is known as an n-type semiconductor. Arsenic 33 is pentavalent impurity. The addition of the pentavalent impurity provides a large number of the electrons in the semiconductor crystal. Answer option A, n-type semiconductor. फिर आता है which of the following when added as an impurity into the silicon produces n-type semiconductor, तो ऑप्शन जाएगा A, phosphorus. When a small amount of the pentavalent impurity added to the pure semiconductor, it is known as the n-type semiconductor. Phosphorus is a pentavalent and silicon is tetravalent. Therefore, when the phosphorus is doped with silicon, it forms a n-type semiconductor. फिर आता है कि in the figure the input is across the terminals A and C and the output is across the terminal B and D. Then the output is, तो Fe input is applied across the A and C and output is taken across the BD. So when the positive cycle is fed to the Fe, D1 and D2, D4 conduct. When the negative cycle is fed to the Fe, D3 and D2 conduct in the same way direction. Output across BD is thus full wave rectified. तो आंसर 44 कितना जाएगा? आंसर आएगा ऑप्शन डी, फुल वेव रेक्टिफाइड. फिर आता है कि when a PN junction diode is reverse bias the flow of the current across the junction is mainly due to, तो आंसर आएगा ऑप्शन बी, ड्रिफ्ट चार्ज के कारण है जो होता है. आंसर आएगा ऑप्शन बी. When a PN junction is said to be reverse bias if the positive terminal of the external battery B is connected to the N side, then the negative terminal of the P side of the PN junction diode. In a reverse biasing, the reverse bias voltage supports the potential barrier BB. Now the magnetic carriers are pulled away from the junction and the depletion region becomes thick. There is no conduction across the junction due to the magnetic carriers. However, a few magnetic carriers falls in the N section and electrons in the P section of the PN junction diode cross the junction after being affected by the high reverse bias voltage. They constitute a current that flow in the opposite direction. So when PN junction is reverse biased, the flow of the current is due to the drifting of the magnetic charge carriers across the junction. A piece of the copper, another type of the germanium are cooled from the room temperature to 80 Kelvin. Then आंसर होगा ऑप्शन डी, the resistance of the copper will decrease while that of the germanium का हो जाएगा increase हो जाएगा. तो semiconductor have the negative temperature coefficient of the resistance. That means the resistance of a semiconductor decrease with increase in the temperature as number of the electrons increase in the conduction bond. Copper has the positive temperature coefficient of the resistance. That means the resistance of the copper increase with increase in the temperature due to the collision of the electron. Hence at 80 Kelvin the resistance of the copper will decrease while that of the germanium क्या हो जाएगा increase होगा. फिर आता है कि डायमंड इज वेरी हार्ड बिकॉज, तो इसका आंसर आएगा ऑप्शन बी, इट हैज ए लार्ज कोहेसिव एनर्जी. द कोहेसिव एनर्जी ऑफ द फुली डिफाइंड एज द एनर्जी रिक्वायर्ड फॉर सेपरेटिंग द कंडेंसर मटेरियल इनटू द आइसोलेटेड फ्री एटम्स. द बॉन्ड एनर्जी इनटू द कार्बन एटम विच डायमंड हैज कोहेसिव एनर्जी ऑफ 7.3 इलेक्ट्रॉन वोल्ट with respect to the separated neutral atom. Due to such high cohesive energy, diamond is very hard. फिर आता है for an electronic ball, the plate current I and the plate voltage V in the space charge limited regions are related to the. तो इसका आंसर क्या जाएगा? इसका आंसर जाएगा ऑप्शन ए कि I is proportional to V के पावर 3/2. यानी the most important characteristic of a vacuum diode is the plate characteristic which gives the relation between the plate voltage and the plate current for a given cathode temperature. It may be noted from the plate characteristic that all the curves are constant at low plate voltage, where the negative space charge is most effective in limiting plate current. This low plate voltage region OA is known as the space charge limited region. In this region, the plate current increases as the plate voltage increases because more positive plate attracts electrons from the space charge at a greater rate. In the space charge limited region, the plate picture is given by the relation I is equal to k v के पावर 3/2. तो I भी मिली एम्पियर में है, I डायरेक्टली प्रोपोर्शनल टू v के पावर 3/2 भी दिया हुआ है. और स्पेस चार्ज लिमिटेड रीजन I is equal to k v के पावर 3/2. यहाँ पर T1, यहाँ पर दिया हुआ T2, where k क्या है तो कांस्टेंट है. फिर आता है which one of the following is the biggest kind of the bonding in the solid? आंसर आएगा ऑप्शन सी, वैन डर वाल. अगला है कि for amplification by a triode the सिग्नल टू बी एम्पलीफाइड गिवन बाय दी. तो इसका आंसर क्या जाएगा? इसका आंसर आएगा ऑप्शन बी, द ग्रिड. पहले इससे पूछता था, अब नहीं पूछेगा. तो यहाँ पर दिया है कि फिगर फॉर द बेसिक डायोड एम्पलीफायर सर्किट द बिग सिग्नल जी इज अप्लाइड इन द ग्रिड सर्किट एंड यूजफुल आउटपुट इज ऑब्टेन्ड अक्रॉस द लोड RL connected in the plate circuit. The bias battery EC ensure the grid to be always negative with respect to cathode. The big signal voltage produces a large change in the plate current as the value of the RL is quite high, therefore a large voltage drop across it. Thus the big signal applied in the grid circuit appears in the amplified form in the plate circuit. फिर आता है the depletion layer in the PN junction region कितना होता है? तो आंसर होगा ऑप्शन बी, डिफ्यूजिंग ऑफ द चार्ज कैरियर. The accumulation of the electric charges of the opposite polarity in the two regions of the junction give rise to an electric field between these regions due to the diffusion of the charge carrier. This electric field opposes the further flow of the electrons from the N region to the P region and that of the holes from the P region to the N region. The electric field sets a potential barrier Vb at the junction which opposes the further diffusion of the free charge carrier into the opposite regions. In the vicinity of the junction, a region is created which is devoid of the free charge carrier and has a immovable ions. This region in which no free charge carriers are available is called the depletion region. This is shown in the figure. The depletion region इस प्रकार होता है p टाइप, ub और इधर दिया हुआ है n टाइप. अगला है कि when a triode is used as an amplifier, the phase difference between the input signal voltage and the output is. So in the triode amplifier, there is a phase difference of the 180 degree between the input, that means the signal voltage, and the output voltage. In other words, the positive half cycle of the signal appears for the amplified negative half in the output, while the negative half cycle of the signal appears for the amplified positive half of the output. This is one the phase reversal. In other words, as the signal is increasing in the negative half cycle, the output is increasing in the positive one. Stands for option B, pi. फिर आता है कि when n type semiconductor is heated, तो इसका आंसर हो जाएगा डी कि नंबर ऑफ इलेक्ट्रॉन्स ऑन द होल्स वजह इंक्रीज करेगा इक्वली. यानी when n type semiconductor is heated, a few whole electron pairs regenerate. When free electron is produced, then the simultaneously whole is also produced. The number of electrons on holes both increase equally. फिर आता है pn junction is said to be forward bias when. तो इसका आंसर क्या आ जाएगा? इसका आंसर आएगा कि when external voltage is applied to the junction in such a direction that it cancels the potential barrier or decreases the potential barrier, thus permitting current flow, it is called the forward biasing. To apply the forward bias, connect the positive terminal of the battery to the p type and negative terminal of battery to the n type as shown in the figure. तो इसका आंसर आएगा ऑप्शन ए कि the positive pole of the battery is joined to the p semiconductor and the negative pole to the n semiconductor. तो आंसर आएगा ऑप्शन ए. फिर आता है कि at absolute zero silicon act as the आंसर आएगा सी insulator की तरह. तो semiconductors have the negative temperature coefficient of the resistance. That means the resistance of the semiconductor decreases with increase in the temperature and vice versa. Silicon is actually an insulator at absolute zero for the temperature, but it becomes a good conductor at high temperature because on giving temperature to the semiconductor, some of the electrons jump from the valence band to the conduction band. अब यहाँ पर ट्रांजिस्टर है, लेकिन ट्रांजिस्टर तो सिलेबस में नहीं है, तो ये सब अब नहीं आ रहे हैं. अब नेक्स्ट फिर आता है एक टॉपिक है जिसे कहते हैं डिजिटल सर्किट. तो इसमें आता है कि विच ऑफ द फॉलोइंग गेट इज कॉल्ड यूनिवर्सल गेट. तो नैंड गेट को है जो यूनिवर्सल गेट कहते हैं. नैंड और नॉर गेट आर कॉल्ड यूनिवर्सल गेट बिकॉज ऑल टाइप ऑफ लॉजिक गेट एंड बुलियन एक्सप्रेशन कैन बी लैड विद द हेल्प ऑफ द नैंड एंड द नॉर गेट. फॉर द लॉजिक गेट फ्रॉम द ट्रूथ टेबल क्या हो जाएगा? तो इसके लिए तो ए है, ए नॉट बी नॉट और ए नॉट प्लस बी नॉट का होल नॉट है. तो इसका बनाएंगे ट्रूथ टेबल, तो ये हो जाएगा ए नॉट प्लस बी नॉट का होल नॉट, यानी ए नॉट यानी प्लस है तो इंटू में आ जाएगा प्रोडक्ट में. तो ए नॉट नॉट बी नॉट नॉट यानी ए इंटू बी आ जाएगा. कहने का मतलब एंड गेट है ये. तो एंड गेट का देख सकते हैं. एंड गेट का होता है क्या? एंड गेट का आता है 0 0 तो आ जाएगा 1, 0 1 तो आ जाएगा 0, तो 0 0 तो फिर आ जाएगा 1 0 तो 0 1 1 तो आ जाएगा 1. तो आंसर इसका कितना जाएगा? आंसर इसका जाएगा ऑप्शन डी. ये अगला है क्वेश्चन कि द सर्किट डायग्राम फोन हेयर कॉरस्पॉन्ड टू द लॉजिक गेट. तो इसमें आ जाएगा कि ये है 1 0 0 फिर यहाँ 6 वोल्ट हो गया, एलईडी हो गया और यहाँ पर 0 आ गया. तो फॉर द सर्किट डायग्राम कैन बिलो इट कैन बी सीन दैट करंट विल फ्लो टू द ग्राउंड इफ एनी ऑफ द स्विच क्लोज्ड, also the LED will only glow when the current flow through it. So that's the truth table for the circuit diagram can be found as circuit diagram in the solution. तो 6 वोल्ट 0 0 तो LED हो गया. तो आउटपुट पाई इक्वल टू दैट ऑफ द नॉर गेट की तरह है. क्यों? क्योंकि एक को बंद करेंगे नॉर गेट की तरह है और नॉर गेट की तरह है. ठीक है, ये हाई वोल्टेज हो गया, लो वोल्टेज हो गया. अगर एक को बंद करेंगे मान लो इसको बंद करते हैं तो भी इस तरफ चल जाएगा, और इसको खुला रखते हैं तो भी चल जाएगा, और इसको खुला रखते हैं इसको बंद करते हैं तो भी चल जाएगा. तो इसमें है कि फ्रॉम द सर्किट डायग्राम गिवन बिलो इट कैन बी सीन दैट द करंट विल फ्लो टू द ग्राउंड इफ एनी ऑफ द स्विच, कोई भी एक स्विच को क्या कर दो, क्लोज कर दो. also the LED will only glow when the current flow through it. ठीक है, तो ये है जो नॉर गेट की तरह इसका है, तो ये हो जाएगा क्या? नॉर गेट हो जाएगा. फिर आता है इसमें इलेक्ट्रिकल इक्विवेलेंट सर्किट है जो डायरेक्ट पूछा हुआ है। ये तो हो जाएगा नैंड गेट की तरह, तो इसका नैंड गेट हो जाएगा। ये है नॉर गेट, देखो नॉर गेट है ये नॉर गेट है, और ये है जो नैंड गेट है। The LED will glow when the current flow through it. That means when the voltage across it is high, the two table can be formed from this. The output by semi that come from the NAND gate. Next है कि in the combination of the following gates the output by can be written as, तो इसमें आ जाएगा A, इसमें आ जाएगा A, फिर आता है A, इसमें कितना आ जाता है, इसमें आ जाता है, यहाँ पे चलते हैं कि A बाय इक्वल टू हो जाएगा A और B है, तो A बार B बार, यहाँ पर B बार A सी इक्वल टू A डॉट बी बार, और यहाँ पर आ जाएगा D इक्वल टू A बार डॉट B, तो बाई इक्वल टू आ जाएगा C प्लस D, यानी A डॉट B बार प्लस A बार डॉट B। आंसर कितना आ जाएगा ऑप्शन बी, A डॉट B बार प्लस A बार डॉट B। फिर आता है कि इन द गिवन इलेक्ट्रिकल वर्क इज इक्वलेंट टू दी, तो इसमें आ जाएगा ऑप्शन सी, नॉर गेट की तरह इक्वलेंट है। आउटपुट बाई ऑफ द नेटवर्क मैच विद दैट ऑफ द नॉर गेट। फिर आता है टू गेट द आउटपुट 1 फॉर द फॉलोइंग सर्किट द करेक्ट चॉइस ऑफ द इनपुट गेट कितना हो जाएगा, to consider the given circle, the alternate Boolean expression for the above logic circuit will be pi is equal to a plus p dot c। तो आंसर आएगा ऑप्शन कितना, आंसर आएगा now let us try with the input a b and c in the option and let see which one of them will give the output 1 at the by। if a बराबर 0, b बराबर 0, c बराबर 0, तो by is equal to कितना आएगा 0। if a बराबर 1, b बराबर 1, c बराबर 0, तो by equal to आ जाएगा 0। if a बराबर 1, b बराबर 0, c बराबर 1, तो by equal to आ जाएगा 1, और यहाँ से निकालें तो by equal to कितना आ जाएगा 0। so we have seen that among the given option only option c is the correct option। output by 1 only when input a is equal to 1, b is equal to 0 और c is equal to 1। तो यहाँ पर क्या आ जाएगा, यहाँ पर आंसर आ जाएगा ऑप्शन सी, ए इज इक्वल टू 1, बी इक्वल टू 0 और सी इज इक्वल टू 1। फिर आता है what is the output by in the following circuit when all the three input a b and c and a b c are first 0 and then 1। तो इसमें आ जाएगा आउटपुट फॉर द गिवन सर्किट गिवन बाय इज इक्वल टू ए बी सी, तो ए इज इक्वल टू बी इक्वल टू सी इक्वल टू 0, बाय 1 इज इक्वल टू आ जाएगा 0 के बार यानी कि 1, और ए इक्वल टू बी इक्वल टू सी इक्वल टू 1, तो बाय 2 इक्वल टू आएगा 1 बार तो आ जाएगा 0। तो आंसर कितना जाएगा, आंसर आएगा ऑप्शन सी 1,0, ऑप्शन सी चला जाएगा 1,0। फिर आता है विच लॉजिक गेट ये प्रिंटेड बाय द फॉलोइंग कॉम्बिनेशन ऑफ द लॉजिक गेट, आंसर आएगा ऑप्शन सी एंड गेट, इससे है जो 4 है। नेक्स्ट है कि द आउटपुट एक्स ऑफ द लॉजिक गेट सर्किट इन द फिगर क्या हो जाएगा, तो एक्स इक्वल टू ए बी के बार यानी ए डॉट बी, एंड नैंड गेट है। इफ द आउटपुट ऑफ द नैंड गेट इज कनेक्टेड टू द इनपुट ऑफ द नॉट गेट मेड फ्रॉम द नैंड गेट बाय ज्वाइनिंग टू इनपुट्स फ्रॉम द गिवन फिगर देन वी गेट बैक एन एंड गेट। तो आंसर कितना जाएगा ऑप्शन सी ए डॉट बी चल जाएगा। इफ द आउटपुट ऑफ ए नैंड गेट इज कनेक्टेड टू द आउटपुट ऑफ ए नॉट गेट फ्रॉम द गिवन गेट देन वी गेट बैक द एंड गेट, तो इसको फिर से नॉट गेट में कनेक्ट करेंगे तो ये क्या हो जाएगा, एंड गेट ही हो जाएगा। अगला क्वेश्चन है कि द फिगर फॉर ए लॉजिक सर्किट विथ टू इनपुट ए एंड बी एंड द आउटपुट सी, द वोल्टेज वेव फॉर्म्स अक्रॉस ए बी एंड सी गिवन है, द लॉजिक गेट दिया हुआ इस प्रकार से। तो फ्रॉम द गिवन वेव फ्रॉम द फॉलोइंग टेबल ट्रूथ टेबल कैन बी फॉर्मड, द ठीक इस तरह से बना सकते हैं इसका ट्रूथ टेबल। द ट्रूथ टेबल ऑपरेंड इज ऑफ द ऑर गेट फॉर द लॉजिक गेट इज द ऑर गेट, आंसर ऑप्शन ए ऑर गेट। फिर है कि सिंबॉलिक रिप्रेजेंटेशन ऑफ द फोर लॉजिक गेट है जो दिखाया हुआ है, पिक आउट वन विच आर फॉर द एंड नैंड एंड द नॉट गेट रिस्पेक्टिवली। तो सबसे पहले एंड के लिए, तो एंड के लिए तो ऑप्शन 2 जाएगा, तो आंसर आएगा ऑप्शन 2 पहला किसमें है सी में, तो यहीं से बन जाएगा। नेक्स्ट है डिवाइस दैट कैन एक्ट एज ए कंप्लीट इलेक्ट्रॉनिक सर्किट इज, तो ऑप्शन बी इंटीग्रेटेड सर्किट। इंटीग्रेटेड सर्किट फॉर द मिनिएचर सर्किट produced within a single crystal of the semiconductor such as silicon. They contain a million or so transistor and resistor of a capacitor. They are widely used in memory circuit, microcomputers, pocket calculators, electronic watches, and account of the low cost and bulk reliability into the specific regions of the semiconductor crystal। फिर आता है to get an output by is equal to 1 from the circuit shown below, the input must be, तो get 1 or the OR gate by the equal to a plus b, get 2 and AND gate by is equal to by the c, तो और a is equal to 1, b is equal to 0, c is equal to 1 will get by is equal to 1, आंसर आएगा ऑप्शन सी 1 0 1। नेक्स्ट है द सिंबॉलिक रिप्रेजेंटेशन ऑफ द फोर लॉजिक गेट, द लॉजिक सिंबल फॉर द और नॉट एंड द नैंड गेट रिस्पेक्टिवली, तो आंसर आएगा ऑप्शन सी 4 2 और 1। द सिंबल्स गिवन इन द प्रॉब्लम है जो इस प्रकार से है, जो पहला वाला जो है वो है नैंड गेट, दूसरा वाला जो है वो है नॉट गेट, तीसरा वाला जो है वो है एंड गेट, और चौथा वाला जो है वो है और गेट। फिर आता है कि द सर्किट इक्वलेंट टू दी, तो सी हो जाएगा नॉर गेट के जैसा इक्वलेंट हो जाएगा। ये नैंड गेट है और ये नॉट गेट है। द गेट सर्किट कैन बी फॉलोड बाय यूजिंग द टू इनपुट्स ए एंड बी। आउटपुट ऑफ द नॉर गेट बाय इज इक्वल टू ए प्लस बी के बार। आउटपुट ऑफ द नैंड गेट बाय टू इक्वल टू बाय वन प्लस बाय टू के बार। तो ए प्लस बी के बार और इंटू ए डॉट बी प्लस बी के बार, तो वो होल बार आ जाएगा, तो इसका आंसर आएगा ए प्लस बी। आउटपुट ऑफ द नॉट गेट बाय इक्वल टू बाय टू के बार इक्वल टू ए प्लस बी के बार एंड विच इज आउटपुट ऑफ द नॉर गेट। फिर आता है कि इन द फॉलोइंग सर्किट द आउटपुट बाय फॉर द ऑल पॉसिबल यूनिट इनपुट ए एंड बी एक्सप्रेस्ड बाय द ट्रूथ टेबल। तो वी कैन सिंप्लीफाई द गेट सर्किट एज ए प्लस बी के बार, तो यहाँ पर करेंगे होल तो आ जाएगा द गेट्स 1 and 2 are NOR gates. The output a plus b whole bar of the gate 1 will appear at the input of the gate 2. The final output is by equal to a plus b whole bar is equal to a plus b. This is the Boolean expression or gate which truth table is given below. तो इसका आंसर कितना जाएगा? इसका आंसर आएगा ऑप्शन डी। ये तो बनाकर ही करना पड़ेगा। नेक्स्ट है कि द फॉलोइंग figure for a logic gate with two inputs A and B and the output C. The voltage waveform of the A, B, AC are shown in the figure. तो द लॉजिक गेट इज, तो इसका आंसर ऑप्शन ए एंड गेट हो जाएगा। द बुलियन एक्सप्रेशन विच सेटिस्फाई द आउटपुट फॉर दिस लॉजिक गेट इज इक्वल टू ए डॉट बी विच इज फॉर द एंड गेट, तो इसका आंसर ऑप्शन ए। नेक्स्ट है कि द आउटपुट ऑफ द ऑर गेट इज 1, तो इसका आंसर ऑप्शन इफ आइदर ऑफ बोथ द इनपुट्स आर 1। तो ऑर गेट है टू इनपुट्स ए एंड बी एंड आउटपुट बाय इट फॉलो ए लॉजिक ऑपरेशन रिप्रेजेंटेड बाय द प्लस द फिट ऑफ बुलियन ऑपरेशन ए प्लस बी इक्वल टू हो जाएगा बाय। फिर है कि फॉलोइंग डायग्राम परफॉर्म्स द लॉजिक फंक्शन ऑफ दी, तो आंसर आएगा ऑप्शन बी एंड गेट का काम करेगा। For our convenience, the output of the first NAND gate is chosen as the x. Output of the first NAND gate x equal to a dot b के बार। तो डी मॉर्गन थ्योरम से a dot b के बार इक्वल टू a बार प्लस b के बार यानी x इक्वल टू a बार प्लस b के बार। तो y इक्वल टू x बार इक्वल टू a बार प्लस b के बार, तो a बार b बार के प्रोडक्ट कर देंगे तो y इक्वल टू a डॉट b। इसे लॉजिक फंक्शन ऑफ एंड गेट। फिर आता है द ट्रूथ टेबल गिवन बिलो, तो डिपेंड्स दी, तो ये किसका ट्रूथ टेबल होगा, तो आंसर आएगा ऑप्शन ए, ये हो जाएगा एंड गेट का ट्रूथ टेबल। So we can see from the truth table that output 1 of the only both inputs are 1. This is possible only for the AND gate. The Boolean expression for the AND gate is y equal to a dot b, which satisfy the truth table 0.0 is equal to 0, 1.0 is equal to 0, 0.1 is equal to 0, और 1.1 is equal to 1. Here symbol dot represents the AND operation. फिर आता है the following circuit represents, तो ये हो जाएगा b JOR gate. Output of the upper AND gate is equal to a bar b. Output of the lower AND gate is equal to a b bar. Output of the OR gate is equal to a bar b plus a b bar. This is the Boolean expression for the JOR gate. फिर आता है which one of the following gates will have an output of the 1, तो आंसर आएगा ऑप्शन सी, ये वाला। तो गेट इज एंड नैंड गेट, इट्स आउटपुट विल बी बाय इज इक्वल टू 1.1 यानी 1 बार इक्वल टू 0। गेट पी इज नॉर गेट, इट्स आउटपुट इज 1 बार 1 प्लस 1 के होल बार 1 बार इक्वल टू 0। गेट सी नैंड गेट, इट्स आउटपुट विल बी 0.1 के बार 0 बार इक्वल टू 1। और गेट डी इज जॉर गेट, इट विल बी आउटपुट भी 0 प्लस इज इक्वल टू 0 और बाय इक्वल टू ए बार प्लस बी ए बार इक्वल टू ए इतना। उसके बाद फिर आता है द फॉलोइंग ट्रूथ टेबल बिलोंग टू विच ऑफ द फॉलोइंग फोर गेट्स, तो द बुलियन एक्सप्रेशन एक्सप्रेस्ड बाय द ट्रूथ टेबल में भी रिटन है बाय इक्वल टू ए बार ए प्लस बी का होल बार। दिस एक्सप्रेशन फॉर द नॉर गेट, और गेट प्लस नॉट गेट, तो द नॉर गेट में भी फोन एज, तो इसका आंसर कैंसन आएगा ऑप्शन ए नॉर। नेक्स्ट है कि द बीच ऑफ द फ्लोइंग गेट्स correspond to the truth table given below, तो आंसर आएगा ऑप्शन ए NAND गेट। ट्रूथ टेबल फॉर द NAND गेट इज डेवलप्ड बाय इन्वर्टिंग द आउटपुट्स AND गेट विथ नॉट गेट। आउटपुट फ्रॉम द NAND गेट इज ऑलवेज 1 एक्सेप्ट ऑल द इनपुट ऑफ द 1। डायग्रामेटिक रिप्रेजेंटेशन ऑफ द NAND गेट है दिखाया है, p इक्वल टू होता है a डॉट b के बार। फिर आता है द फ्लोइंग ट्रूथ टेबल correspond to the logic gate, तो आंसर आएगा ऑप्शन बी और गेट की तरह। इट इज क्लियर फ्रॉम द ट्रूथ टेबल दैट आउटपुट इज हाई इफ एनी और ऑल of the inputs are high. The only way to get a low output is by the having all inputs low. The output by or gate is low when all the inputs are low. The output by of an OR gate is high if any or all the inputs are high. For this truth table is of the OR gate. अब यहाँ पर है जो ये PY किसका होता है, अब इसका देखेंगे NCERT सेमीकंडक्टर इलेक्ट्रॉनिक्स मटेरियल्स डिवाइस एंड सिंपल सर्किट्स का देखेंगे NCERT। तो इसमें आता है NCERT में कि डिवाइसेज, NCERT में आता है कि डिवाइस इन विच कंट्रोल फ्लो ऑफ इलेक्ट्रॉन्स कैन बी ऑब्टेन्ड आर द बेसिक बिल्डिंग ब्लॉक्स ऑफ ऑल इलेक्ट्रॉनिक सर्किट्स बिफोर द डिस्कवरी of the transistor in the 1948. Such devices are mostly vacuum tubes, also called as the valves, like the vacuum diode which had two electrodes, namely the anode, often called as the plate, and cathode diode which had the three electrodes, cathode, plate and the grid, the tetrode and the pentode respectively with 4 or 5 electrodes. In the vacuum tube, the electrons are supplied by a heated cathode and the controlled flow of these electrons in the vacuum is obtained by varying the voltage between these different electrodes. Vacuum is required in the inner inter-electrode space, otherwise the moving electrons may lose their energy on collision with the air molecule in their path. In the devices, the electrons can flow only from the cathode to the anode, that means only one direction. Therefore, such devices are generally referred to as the valves. The vacuum tube devices are bulky, consume high power, operate generally at high voltage 4 volt, and have limited life and low reliability. The seeds of the development of the modern solid state semiconductor electronics goes back to the 1940s when it was realized that some solid state semiconductor and their junction offer the possibility of controlling the number and the directions of the flow of the charge carrier through them. Simple excitation like the light, heat, or the small applied voltage can change the number of the mobile charge carriers in the semiconductor. Note that supply and the flow of the charge carriers in the semiconductor device are within the solid itself. While in the earlier vacuum tubes or valves, the mobile carry electrons were obtained from a heated cathode and they were made to flow in an evacuated space or the vacuum. No external heating or large evacuated space is required for the semiconductor devices. They are small in the size, consume low power, operate at low voltage, and have the long life and high reliability. Even the cathode ray tube CRT is used in the television and computer monitors, which work on the principles of the vacuum tubes, are being replaced by the LCD monitors with supporting solid-state electronics. Much before the full implication of the semiconductor devices was firmly understood, a naturally occurring crystal of the galena lead sulfide PBS with a metal point contact attached to it was used as a detector of the radio wave. In the following section, we will introduce the basic concept of the semiconductor physics and discuss some semiconductor devices like the junction diode, a 2-electrode device, and bipolar junction diode, a transistor 3-electrode device. A few circuit illustrating the application will also be described. फिर आता है classification for the metals, connectors, and the semiconductors. So, on the basis of the conductivity, on the basis of the relative value of the electric conductivity sigma or the resistivity rho equal to 1 by sigma, the fluids are broadly classified as metals. They possess very low resistivity or high conductivity. रो जो होता है 10⁻² से 10⁻8 ओम मीटर होता है और सिग्मा होता है 10⁻2 से 10⁻8 फैमन पर मीटर इनवर्स. सेमीकंडक्टर दे हैव द रेसिस्टिविटी और कंडक्टिविटी इंटरमीडिएट टू द मेटल्स एंड इंसुलेटर. तो रो हो जाएगा 10⁻5 to 10⁻6 ओम मीटर और सिग्मा हो जाएगा 10⁻5 to 10⁻6 फैमन मीटर इनवर्स. इंसुलेटर दे हैव हाई रेसिस्टिविटी और लो कंडक्टिविटी. तो रो हो जाएगा 10⁻11 to 10⁻19 सिग्मा मीटर और सिग्मा हो जाएगा 10⁻11 से 10⁻19 फैमन मीटर इनवर्स. The value of the rho and the sigma given above are indicative of the magnitude and could go well outside and range as well. Relative value of the resistivity are not the only criteria for distinguishing metals, insulators, and the semiconductors from each other. There are some other differences which will become clear as we go along in this chapter. So our interest in this chapter is the study of the semiconductors, which could be elemental semiconductors, silicon and germanium. Compound semiconductors example are the inorganic GA, FDF, GAF, DFE, INP, etc. Organic anthracene, doped phthalocyanins, etc. Organic polymers, polypyrrole, polyaniline, polythiophene, etc. Most of the currently available semiconductor devices are based on the elemental semiconductor of the silicon or germanium and the compound inorganic semiconductors. However, after 1990, few semiconductor devices using organic semiconductors and semiconducting polymers have been developed, signaling the birth of a futuristic technology of the polymer electronics and the molecular electronics. In this chapter, we will restrict ourselves to the study of the inorganic semiconductors, particularly elemental semiconductor, Fe, silicon, and the germanium. The general concept introduced here for the discussing the elemental semiconductors by and large apply to the most of the conductors, compound semiconductor as well. But on the basis of the energy bands, so according to the Bohr atomic model, and in an isolated atom, the energy of any of its electron is divided by the orbit in which it revolves. But when the atoms come together to form a solid, they are close to each other. So, the outer orbits of the electron from the neighboring atoms would come very close or could even overlap. This would make the nature of the electron's motion in a solid very different from that in the isolated atom. Inside the crystal, each electron has a unique position and no two electrons are seen exactly the same pattern of the surrounding charges. Because of this, each electron will have a different energy level. These different energy level with the content of energy variation form what are called as the energy bands. The energy bands, which include the energy levels of the valence band, are called the valence band. The energy bands of the valence band is called the connection band. With no external energy, all the valence electrons will reside in the valence band. If the lowest level in the connection band happens to be lower than the highest level of the valence band, electrons from the valence band can be easily moved into the connection band. Normally, the conduction band is empty, but when it overlaps on the valence band, electrons can move freely into it. This is the case with the metallic conductor. If there is some gap between the conduction band and the valence band, electrons in the valence band all remain bound and no free electrons are available in the conduction band. This makes the material an insulator, but some of the electrons from the valence band may gain external energy to cross the gap between the conduction band and the valence band. Then these electrons will move to the conduction band. At the same time, they will create vacant energy levels in the valence band where the other valence band can move. Therefore, the process creates the possibility of conduction due to the electrons in the conduction band as well as due to the vacancy in the valence band. फिर आगे है कि let us consider what happens in the case of the silicon or the germanium crystal containing an atom. For the silicon, the outermost orbit is the third orbit in number 3, while for the germanium it is fourth orbit in number 4. The number of the electrons in the outermost orbit is 4, 2s and 2p electrons, hence the total number of the outer electrons in the crystal is 4n. The maximum possible number of electrons in the outer orbit is 8. So for the 2n, for the 4n valence electron, there are 8n available in a GIF state. These 8n discrete energy levels can either form a continuous band or they may be grouped in different bands depending upon the distance between the atoms in the crystal. At the distance between the atoms in the crystal lattice of the silicon and the germanium, the energy band of these 8n state is split apart into two which are separated by energy gap. The lower band, which is completely occupied by the foreign valence electron at a temperature of the absolute zero, is called the valence band. The other band consisting of the foreign energy state, called the conduction band, is completely empty at the absolute zero. The lowest energy level in the conduction band is shown by the EC, and the highest energy level in the valence band is shown in the EV. Above EC and below EV, there are large number of the closely specified energy level. The gap between the top of the valence band and the bottom of the conduction band is called the energy band gap. It may be large, small, or zero depending upon the material. These different situations are depicted in the figure 14.2 and described below. Case 1, this refers to the situation as shown in figure 14.2a. One can have a metal either when the conduction band is partially filled with the valence band is partially empty, or when the conduction band and valence bands overlap. When there is overlap, electrons from the valence band can easily move into the conduction band. This situation makes a large number of the electrons available for the electrical conduction. When the valence band is partially empty, electrons from its lower level can move to the higher level, making conduction possible. Therefore, the resistance of the such material is low or conductivity is high. अब यहाँ पर दिया हुआ एम्प्टी, ये दिया हुआ foreign state, ये filled हो गया. The infinitely large number of the states be occupied by the 2 electrons at 0 Kelvin. The energy band position in the semiconductor at 0 Kelvin. The upper band, called the semiconduction band, consists of infinitely large number of the closely specified energy state. The lower band, called the valence band, consists of a closely specified completely filled energy state. फिर आता है यहाँ पर दिया हुआ है इलेक्ट्रॉन एनर्जी, यहाँ पर दिया हुआ कंडक्शन बैंड, यहाँ पर दिया हुआ बैलेंस बैंड, और यहाँ पर दिया इलेक्ट्रॉन का एनर्जी एम्प्टी कंडक्शन बैंड, और यहाँ पर दिया हुआ बैलेंस बैंड. तो ईजी जो है ग्रेटर देन 3 इलेक्ट्रॉन वोल्ट आ जाएगा. फिर आता है इलेक्ट्रॉन एनर्जी यहाँ पर हो जाएगा ओवरलैपिंग कनेक्शन बैंड ईजी इक्वल टू 0 और बैलेंस बैंड दिया हुआ है. फिर ईजी लेस देन 3 इलेक्ट्रॉन वोल्ट ईसी और ईवी दिया हुआ है. फिर आता है कि डिफरेंस बिटवीन दी एनर्जी बैंड्स, मेटल्स, इंसुलेटर्स एंड द सेमीकंडक्टर्स. तो case 2 आता है कि in this case as shown in the figure 14.2 be a large band gap EG exists, EG greater than 3 electron volt. There are no electrons in the conduction band and therefore the no electrical conduction is possible. Note that energy gap is so large that electrons cannot be excited from the valence band to the conduction band by the thermal excitation. This is the case of the insulator. The situation is shown in the figure 14.2c. Here a finite but a small band gap EG less than 3 electron volt exists. Because of the small band gap at the room temperature, some electrons from the valence band can acquire enough energy to cross the energy gap and enter the conduction band. These electrons, though small in the number, can move into the conduction band. Hence, the resistance of the semiconductor is not high as that of the insulator. In this section, we have made a broad classification of the metal, conductors, and the semiconductors. In this section, which you follow, you will learn the conduction process in the semiconductor. तो यहाँ पर दिया हुआ है 3-dimensional diamond like crystal of the carbon, silicon or germanium with respective lattice spacing A to the 3.6, 5.43 and 5.66 ampere angstrom for the intrinsic semiconductor. So before take most common case of the Ge and the Fi, whose lattice factor is shown. These structures are called the diamond-like structure. Each atom is surrounded by a 4 nearest neighbor. We know that Fi and G have 4 valence electrons in its crystalline structure. Every silicon or germanium atom tend to share one of its 4 valence electrons with each of its 4 nearest neighbor atom, and also to take share of the 1 electron from each neighbor such neighbor. These shared electron pairs are referred to as forming a covalent bond or simply a valence bond. The two shared electrons can be assumed to shuttle and back and forth between the associated atoms, holding them together strongly. Figure 14.4 schematically for two-dimensional representation of the silicon or germanium structure for a figure which oversimplify the covalent bond. It also for a light picture in which no covalent bonds are broken. Such a situation arises at low temperature. As the temperature increases, more thermal energy becomes available to these electrons, and some of these electrons may break away, breaking free electrons contributing to the conduction. The thermal energy effective energy only a few times in the crystalline lattice and creates vacancy in the bond as shown. The neighborhood from which the free electrons with charge -q has come out leaves a vacancy with an effective charge of the +q. This vacancy with the effective positive electronic charge is called a hole. The hole behaves as an apparent free particle with effective positive charge. In the intrinsic semiconductor, number of the electrons n is equal to the number of the holes nh, that is n is equal to nh equal to ni, where ni is the intrinsic carrier concentration. Semiconductors possess the unique property in which they, apart from the electrons, the holes also move. Suppose there is a hole at the phi 1 as shown in the figure. The movement of the holes can be visualized as shown in the figure. And electrons from the covalent bond at the phi 2 jump the vacant phi. After such a jump, the hole is at the phi 2 and the phi 1 has now electron. Therefore, apparently the hole has moved from the phi 1 to the phi 2. Note that electron originally set free is not involved in this process of the hole motion. The free electron moves completely independently as conduction electron and gives rise to an electron current IE under the applied electric field. Remember that the motion of the hole is only a convenient way of describing the actual motion of the bond electrons. Whenever there is an empty bond anywhere in the crystal, under the action of electric field, these holes move towards the negative potential, giving the hole current IH. The total current I is the sum of the electron current I and the hole current IH. तो I is equal to I plus IH हो जाता है. यहाँ पर the schematic two-dimensional representations of the silicon or the germanium structure showing covalent bonds at the low temperature, all bonds intact. +4 symbol indicates the inner core of the silicon or the germanium. यहाँ पर जो silicon covalent bonds और bonding electrons है ये दिखाए हुए. So it may be noted that apart from the process of generation of the conduction electrons and the holes, a simultaneous process of recombination occurs in which the electron recombine with the holes. At equilibrium, the rate of the generation is equal to the rate of the recombination of the charge carrier. The recombination occurs due to an electron colliding with a hole. तो यहाँ पर दिखाया हुआ schematic model of the regeneration of the hole at the phi 1 and conduction electron due to thermal energy at a moderate temperature. Simplified implications of the possible thermal motion of a hole. The electrons from the lower left hand covalent to the earlier hole phi 1, leaving a hole at the phi indicating an apparent movement of this hole from the phi 1 to the phi 2. यहाँ पर जो thermally generated free electron silicon और the germanium का जो दिखाया हुआ है. So an intrinsic semiconductor will behave like an insulator at T equal to 0 Kelvin. It is a thermal energy at higher temperature T greater than 0 Kelvin which excites some electrons from the valence band to the conduction band. The thermally excited electrons at T greater than 0 Kelvin partially occupy the conduction band. Therefore, the energy band diagram of an intrinsic semiconductor will as shown in the figure 14.6b. Here some electrons are shown in the conduction band. These have come from the valence band having equal number of the holes there. अब यहाँ पर दिया हुआ है an intrinsic semiconductor at T equal to 0 Kelvin. We have selected the insulator at T greater than 0 Kelvin for thermally generated electron hole pair. Filled circle represent the electrons and empty circle represent the holes. फिर दिया जाता है कि कार्बन सिलिकॉन एंड जर्मेनियम have the same lattice structure. Why is C insulator while Fi and G intrinsic semiconductor? The four bonding conductor electrons of the carbon, silicon, or G lie respectively in the second, third, and the fourth orbit. Hence, for energy required to take out an electron from these atoms, that means ionization Eg will be least for the G followed by the Fi and the highest for the Phi. Hence, the number of the electrons for the connection in the G and the Phi are significant, but negligibly small for the Phi. अब इसके आगे बात करते हैं एक्सट्रिंसिक सेमीकंडक्टर की. So the connectivity of an intrinsic semiconductor depends on its temperature, but at room temperature its connectivity is very low. As such, no important electronic device can be developed using these semiconductors. Hence, there is necessity of improving their connectivity. This can be done by making use of the impurities. When a small amount, say a few parts per million ppm of the suitable impurity is added to the pure semiconductor, the conductivity of the semiconductor increased manifold. Such materials are known as the extrinsic semiconductor or the impurity semiconductors. The deliberate additions of a dissolvable impurity is called a doping, and the impurity atoms are called as the dopants. Such material is also called a doped semiconductor. The dopant certifies that it does not distort the original pure semiconductor lattice. It occupies only very few of the original semiconductor from atoms found in the crystal. A necessary condition to attain this is that the size of the dopant and the semiconductor atom should be nearly the same. There are two types of the dopants used in the doping: the tetravalent silicon or the germanium. Pentavalent valency 5 like the arsenic and antimony, phosphorus, P, etc. Or the trivalent valency 3 like the indium, boron, aluminum, etc. Before now discuss how the doping change the number of the charge carriers and hence the conductivity of the semiconductor. Silicon or germanium belongs to the fourth group in the periodic table, and therefore we choose the dopant element from the nearby fifth or the third group, expecting and taking care that the size of the dopant atom is nearly the same as that of the silicon or germanium. Interestingly, the pentavalent and the trivalent dopants of the silicon or germanium give two entirely different types of the semiconductor as discussed below. तो यहाँ पर दिखा हुआ है कि पेंटावलेंट डोनर एटम्स आर्सेनिक Fb and the P doped for the tetravalent silicon or germanium giving n-type semiconductor, and the commonly used schematic representations of the n-type material which show only the fixed course of the subsequent donor atom with one additional effective positive charge and associated with the extra electron. अब यहाँ पर दिखा हुआ है अनबॉन्डेड फ्री इलेक्ट्रॉन्स डोनेटेड बाय द पेंटावलेंट +5 वैलेंसी एटम, और यहाँ पर इलेक्ट्रॉन्स दिया हुआ है, डोनर को दिया हुआ है. अब आता है n type semiconductor. तो suppose we dop silicon or germanium with the pentavalent element H1 in the figure, when an atom of the +5 valency element occupy the position of an atom in the crystal lattice of the silicon. Four of its electron bond with the four silicon neighbors, while the fifth remains very weak bonded to its parent atom. This is because of the four electrons participating in the bonding are seen as a part of the effective core of the atom by the fifth electron. As a real ionization energy required to fit this electron free is very small, and even at room temperature it will be free to move in the lattice of the semiconductor. For example, the energy required is 0.01 electron volt for the germanium and 0.05 electron volt for the silicon to separate this electron from its atom. This in contrast to energy required to jump for the forbidden band, about 0.12 electron volt for the germanium and about 1.1 electron volt for the silicon at room temperature in the intrinsic semiconductor. Thus, the pentavalent dopant is donating one extra electron for the connection and hence is known as the donor impurity. The number of electrons made available for the connection by the dopant atoms depends strongly upon the doping level and is independent of any increase in the ambient temperature. On the other hand, the number of the free electrons with an equal number of the holes generated by the silicon atom increases weakly with the temperature. In a doped semiconductor, the total number of the connection electrons N is due to the electrons contributed by the donors and those generated by intrinsically, while the total number of the holes NH is only due to the holes from the intrinsic source, but the rate of the recombination of the holes would increase due to the increase in the number of electrons. As a result, the number of the holes would get reduced further. Thus, with the proper level of doping, the number of the connection electrons can be made much larger than the number of the holes. Hence, in an intrinsic semiconductor doped with pentavalent impurity, electrons become the magnetic carriers and the holes the magnetic carriers. These semiconductors are therefore known as the n-type semiconductor. For the n-type semiconductor, we have Ne is much greater than NH. अब बात करते हैं p-type semiconductor की. तो this is obtained when silicon or germanium doped with a trivalent impurity like the aluminum, boron or indium. The dopant has one valence electron less than the silicon or germanium, and therefore this atom can form the covalent bonds with the neighboring three silicon atom, but does not have any electron to offer to the fourth silicon atom. So the bond between the fourth neighbor and the trivalent atom has a vacancy or hole at its own. Since the neighboring silicon atom in the lattice bonds an electron to place in the hole, an electron in the outer orbit of the atom in the neighborhood may jump to fill this vacancy, leaving a vacancy or a hole of its own side. Thus, the hole is available for the connection. Note that a trivalent foreign atom becomes effectively negatively charged when it shares fourth electron with a neighboring silicon atom. Therefore, the dopant atom of the p-type material can be treated as a core of one negative charge along with associated hole as shown. It is obvious that one separate atom gives one hole. These holes are in addition to the intrinsically generated holes, while the source of the connection electrons is only the intrinsic generation. Thus, for the such material, the holes are the magnetic carriers and the electrons are the magnetic carriers. Therefore, the extrinsic semiconductors doped with trivalent impurity are called the p-type semiconductor. For p-type semiconductor, the recombination process will reduce the number of the Ni of the intrinsically generated electrons to Ne. We have for the p-type semiconductors, Nh is much greater than the Ne. Note that the crystal maintains all over charge neutrality as the charge of the additional charge carriers is just equal and opposite to that of the ionized cores in the lattice. In the extrinsic semiconductor, because of the abundance of the magnetic current carriers, the magnetic carriers produced thermally have more chance of meeting magnetic carriers and thus getting destroyed. Hence, the dopant by adding a large number of these carriers for one type, which become the magnetic carriers, indirectly helps to reduce the intrinsic concentration of the magnetic carriers. The semiconductor energy band of structure is affected by the doping. In the case of the extrinsic semiconductor, additional energy of states due to the donor impurity ED and the subtrate impurity EA also exist. In the energy band diagram of the N-type semiconductor, the total energy level ED is slightly below the bottom issue of the conduction band, and electrons from this level move into the conduction band with a very small supply of the energy. At room temperature, most of the donor atoms get ionized, but very few, 10^12 atoms of the silicon get ionized. So for the conduction band, we have most electrons coming from the donor impurity as shown in the figure 4.9. Similarly, for the p-type semiconductor, the effector energy level EA is slightly above the top EV of the valence band as shown in the figure, with very small supply of energy, and electron from the valence band can jump to the level EA and annoy the effector negatively. Alternatively, we can also say that with very small supply of energy, the hole from the level EA sinks down into the valence band, electrons rise up and holes fall down when they gain the external energy. At room temperature, most of the effector atoms get ionized, leaving holes in the valence band. Thus, at room temperature, the density of the holes in the valence band is predominantly due to the impurity in the extrinsic semiconductor. The electron and the holes concentration in the semiconductor in the thermal equilibrium is given by N into Nh equal to Nik square. Though the above description is grossly approximate and hypothetical, it helps in understanding the difference between the metals, insulators, and the semiconductors, extrinsic and intrinsic, in a simple manner. The difference in the resistivity of the carbon, silicon, and the germanium depends upon the energy gap between the conduction and valence band. For the carbon, diamond, silicon, and the germanium, the energy gap are the 5.4 electron volt, 1.1 electron volt, and 0.1 electron volt, respectively. Fn also is a group of 4 elements, but is a metal because the energy gap in it is 0 electron volt. अब यहाँ पर दिए हुए है ट्राईवैलेंट एक्सेप्टर एटम इंडियम एल्युमिनियम बोरॉन एटसेट्रा doped in a tetravalent silicon or the germanium lattice giving p-type semiconductor. Commonly used schematic representation for the p-type material which show only the fixed core of the fixture interceptor with one effective additional negative charge and its associated hole. अब यहाँ पर दिखाए हुए है one thermally generated electrons hole pair plus 9 from the donor atom T greater than 0 Kelvin और energy bands N-type semiconductor at T greater than 0 Kelvin, P-type semiconductor at T greater than 0 Kelvin है जो दिखाए हुए. फिर आता है कि suppose a pure silicon crystal has 5 × 10⁻28 atoms per meter cube. It is doped by the 1 ppm concentration of the pentavalent arsenic. Calculate the number of the electrons and the holes given that Ni equal to 1.5 × 10⁻−15 per meter cube. Note that the thermally generated electrons Ni equal to 10⁻15 per meter cube are negatively smaller compared to those produced by the doping. Therefore, N is equal to Nd. Since N into Nh equal to Nik square, the number of the holes Nh equal to 4.5 × 10⁻9 per meter cube. फिर आता है PN junction. तो a PN junction is the basic building block of many semiconductor devices like the diode transistor. A clear understanding of the junction behavior is important to analyze the working of the other semiconductor devices. We will now try to understand how a junction is formed and how the junction behaves under the influence of the external applied voltage, also called the bias. फिर आता है PN junction formation. To consider a thin p-type silicon PFI semiconductor wafer by adding precisely a small quantity of the pentavalent impurity, part of the PFI wafer can be converted into NFI. There are several processes by which a semiconductor can be formed. The wafer now contains P region and N region and the metallurgical junction between P and N region. Two important processes occur during the formation of PN junction: diffusion and the drift. We know that in the N-type semiconductor, the concentration of electron, number of electrons per unit volume is more compared to the concentration of the hole. Similarly, in the P-type semiconductor, the concentration of hole is more than the concentration of the electron. During the formation of a PN junction, and due to the concentration of gradient P and N side, hole diffuse from the P side to the N side, PN, and electrons diffuse from the N side to the P side, NP. This motion of the charge carrier gives rise to the different current across this junction. When an electron diffuses from N to P, it leaves behind an ionized donor on the N side. This ionized donor positive charge is immovable as it is bonded to the surrounding atom. As the electrons continue to diffuse from N to P, a layer of the positive charge or the positive space charge region on the N side of the junction is developed. Similarly, when the hole diffuses from the P to the N, due to the concentration gradient, it leaves behind an ionized acceptor negative charge which is immobile, and the hole continue to diffuse a layer of negative charge or a negative space charge region on the P side of the junction is developed. This space region on the other side of the junction get together is known as the depletion region, and the electrons and the holes taking part in the initial movement across the junction depleted the region of its free charge. The thickness of the depletion region is of the order of the 1/10 of the micrometer due to the positive space charge region on the N side of the junction and negative space charge region on the P side of the junction. An electric field directed from the positive charge towards negative charge develops due to this field. An electron on the P side of the junction moves to the N side and a hole on the N side of the junction moves to the P side. The motion of the charge carried due to the electric field is called the drift. The drift current which is opposite in the direction to the diffusion current of starts. Initially, diffusion current is large and drift current is small. As the diffusion current process continues, the space charge region on the other side of the junction extend, increasing the electric field strength and hence the drift current. This process continues until the diffusion current equals the drift current. If a p-n junction is formed in the p-n junction under equilibrium, there is no net current. The loss of the electrons from the n region and the gain of the electrons from the p region cause a difference of the potential across the junctions of the two regions. The polarity of this potential is such as to oppose the further flow of the carrier for the condition of the game exist. Figure 4.11 shows that p-n junction at equilibrium and the potential of the junction. The n material has lost electrons and the p material has acquired electrons. The n material is thus positive relative to the p material. Since the potential tends to prevent the movement of the electrons from the n region into the p region, it is often called as the barrier potential. Can we take one slab of a p-type semiconductor and physically join it to another n-type semiconductor to get a p-n junction? No, any slab, however flat, will have a roughness much larger than the interatomic crystal of pressure 215 angstrom, and hence continuous contact at the atomic level will not be possible. The junction will have a discontinuity for the flowing charge carriers. फिर यहाँ पर दिखाया हुआ है कि डायोड अंडर द इक्विलिब्रियम भी इक्वल टू 0, बैरियर पोटेंशियल अंडर नो बायस दिखाया हुआ है. फिर यहाँ पर दिखाया हुआ है सेमीकंडक्टर डायोड सिंबल फॉर द पीएन जंक्शन डायोड दिखाया हुआ है. ये हो गया मेटेलिक कॉन्टैक्ट डिप्लेशन रीजन और ये हो गया मेटेलिक कॉन्टैक्ट पीएन है जो दिखाया हुआ है. इसके आगे फिर आता है सेमीकंडक्टर डायोड. तो इसमें है कि सेमीकंडक्टर डायोड is basically a PN junction with a metallic contact provided at the end for the application of an external voltage. It is a two-terminal device. A PN junction diode is symbolically painted as shown in the figure 14.1 to be. The directions of the arrow indicates the conventional directions of the current when the diode is under forward bias. The equilibrium barrier potential can be altered by applying an external voltage B across the diode. The switches of a PN junction diode under the equilibrium without bias is shown in the figure 14.11a and the B. PN junction diode under the forward bias. So, when an external voltage B is applied across a semiconductor diode such as that P side is connected to the positive terminal of the battery and the N side to the negative terminal, it is said to be forward bias. The applied voltage mostly drops across the depletion region and the voltage drop across the P side and the N side of the junction is negligible. This is because the resistance of the depletion region, a region where there are no charges, is very high compared to the resistance of the N side and the P side. The directions of the applied voltage B is opposite. Built-in potential V0 as a result, the depletion layer width decreases and the barrier height is reduced. The effective barrier height under the forward bias is V0 minus V. If the applied voltage is small, the barrier potential will be reduced only slightly below the equilibrium value and only a small number of carrier in the material, those that happen to be in the uppermost energy levels, will possess enough energy to cross the junction, so the current will be small. If we increase the applied voltage definitely, the barrier height will be reduced and more number of the carrier will have the required energy. Thus the current increases. Due to the applied voltage, the electrons from the N side cross the depletion region and reach the P side, where they are minority carriers. Similarly, holes from the P side cross the junction and reach the N side, where they are the minority carriers. This process under the forward bias is known as the magnetic carrier junction. At the junction boundary on the each side, the magnetic carrier concentration increases significantly and compared to the location far from the junction. Due to this concentration gradient, the injected electrons on the P side diffuse from the junction edge of the P side to the other end of the P side. Likewise, the injected hole on the N side diffuse from the junction edge of the N side to the other end of the N side. This motion of the charge carrier on the other side gives rise to the current. The total diode forward current is the sum of the whole diffusion current and the conventional current due to the electron diffusion. The magnitude of this current is usually in the milliampere. फिर आता है PN junction diode under the reverse bias. तो when an external voltage B is applied across the diode such that the N side is positive and the P side is negative, it is said to be reverse bias. The applied voltage mostly drops across the depletion region. The directions of the applied voltage is same as the directions of the barrier potential. As a result, the barrier height increases and the depletion region widens due to the change in the electric field. The effective barrier height under the reverse bias V0 plus V. This suppresses the flow of the electrons from the N to P and holes from the P to N. The diffusion current decreases enormously compared to the diode under the forward bias. The electric field directions of the junctions is such that if the electrons on the P side or the holes on the N side in the random motion come close to the junction, they will shift on its magnetic zone. This drift of the carriers gives rise to the current. The drift current is of the order of the few microampere. This is quite low because it is due to the motion of the carriers from their minority side to the majority side across the junction. The drift current is also under the forward bias but is negligible microampere when compared to the current due to the injected carriers, which is usually in the milliampere. Diode reverse current is not very much dependent on the applied voltage. Even a small voltage is sufficient to shift the minority carriers from the one side of the junction to the other side of the junction. The current is not limited by the magnitude of the applied voltage but is limited due to the concentration of the magnetic carrier on the other side of the junction. The current under the reverse bias is essentially voltage independent into a critical reverse bias voltage known as the breakdown voltage VBR. When the V is equal to VBR, the diode reverse current increases sharply. Even a slight increase in the bias voltage causes a large change in the current. If the reverse current is not limited by the external circuit below the rated value specified by the manufacturer, the PN junction will get destroyed. Once it exceeds the rated value, the diode gets destroyed due to the overheating. This can happen even for the diode under the forward bias if the forward current exceeds the rated value. The circuit arrangement for the studying the VI characteristic of a diode, the variations of the current as a function of the applied voltage is shown. The battery is connected to the diode through the potentiometer or the rheostat so that the applied voltage to the diode can be changed. For different values of the voltage, the value of the current is noted. A graph between the V and I is obtained. Note that in the forward bias measurement, V is a millimeter ammeter since the expected current is large as explained in the earlier section, while micrometer is used in the reverse bias to measure the current. You can see figure 14.16 is that in the forward bias, the current first increases very slowly, almost linearly, till the voltage across the diode across a certain value. After the characteristic voltage, the diode current increases significantly exponentially, even for a very small increase in the diode bias voltage. This voltage is called the threshold voltage or the cut-in voltage, 0.2 V for the germanium diode and 0.1 for the silicon diode. For the diode in the reverse bias, the current is very small in the microampere and almost remains constant with the change in the bias. It is called the reverse saturation current. However, for the special cases at very high reverse bias breakdown voltage, the current suddenly increases. This special action of the diode is discussed later in the section 14.8. The general purpose diodes are not used beyond the reverse saturation current region. There were discussions for that the PN junction diode primarily allow the flow of the current only in the one direction, forward bias. The forward bias resistance is low compared to the reverse bias resistance. This property is used for the rectification of the AC voltage. Discussed in the next section. For the diode, we define a quantity called the dynamic resistance as the ratio of the small voltage in the voltage delta V to a small change in the current delta I. तो RT is equal to delta V by delta I. अब यहाँ पर दिया हुआ है experimental circuit arrangement of studying the VI characteristic of a PN junction diode as in the forward bias, in the reverse bias, typical VI characteristic of a silicon diode का जो दिखाए हुए यहाँ पर हो गया I जो हो गया ये हो गया मिली एम्पियर में, फिर वोल्ट और I हो गया माइक्रो एम्पियर में. फिर यहाँ पर दिखाए हुए है वोल्ट मीटर, मिली एमीटर और स्विच. यहाँ पर वोल्ट मीटर, PN, माइक्रो एमीटर और स्विच दिखाए हुए है बी में. फिर आता है कि डायोड एंड द रिवर्स बायस वेरिएबल पोटेंशियल अंडर द रिवर्स बायस है जो दिखाए हुए है. तो यहाँ पर दिखाया हुआ आर डी इजिकल टू डेल्टा वी बाई डेल्टा आई और द बी आई करेक्टरिस्टिक ऑफ सिलिकॉन डायोड एज फोन इन द फिगर 14.17 calculate the resistance of the diode ID equal to 50 milliampere and VD equal to minus 10 volt. Considering the diode characteristic of a straight line between the I power 10 milliampere and I power 20 milliampere passing through the origin, we can calculate the resistance using the Ohm's law. For the curve I is equal to 20 milliampere, V is equal to 0.8 volt, I equal to 10 milliampere, V equal to 0.5 volt. R F फॉरवर्ड हो जाएगा डेल्टा वी बाई डेल्टा यानी 0.1 वी बाई 10 मिलीएम्पियर यानी कि 10 ओम. फ्रॉम द कर्व एट V इक्वल टू माइनस 10 वोल्ट, I इक्वल टू माइनस 1 म्यू एम्पियर. Therefore, RB is equal to 10 volt by 1 milliampere and 1 गुना 10 minus 4 ओम. और अब इसका आगे फिर है applications of the junction diode as a rectifier. So from the VI characteristic of a junction diode, we see that it allow all current to pass only when it is forward bias. So if the alternating voltage is applied across a diode, the current voltage flow only in that part of the cycle when the diode is forward bias. This property is used to rectify the alternating voltage and therefore the circuit used for this purpose is called the rectifier. In an alternating voltage applied across a diode in the phase with a load, a pulsating voltage will appear across the load only during the half cycle of the AC input during which the diode is forward bias. Such a rectifier circuit as shown in the figure 14.1 is called the half wave rectifier. The secondary of the transformer supply the desired AC voltage across the terminal A and B. When the voltage is at A is positive, the diode is forward bias and it conducts. When A is negative, the diode is reverse bias and it does not conduct. The reverse saturation current of a diode is negligible and can be considered equal to the zero for the practical purpose. The reverse breakdown voltage of the diode must be sufficiently higher than the peak FE voltage at the secondary of the transformer to protect the diode from the reverse breakdown. फिर बोलता है कि therefore in the positive half cycle of the FE the recurrent through the load resisting the RL and B get an output voltage as shown in the figure 14.18b. Whereas there is no current in the negative half cycle, in the next positive half cycle again we get the output voltage. Thus with the output voltage, though of tail bearing, is restricted to only to one direction and is said to be rectified. Since the rectified output of the circuit is only for the half of the input FE wave, it is called the half wave rectifier. The circuit along using two diodes shown in the figure 14.19a gives the output rectified voltage corresponding to both the positive as well as the negative half of the AC cycle. Hence it is known as the full wave rectifier. Here the P side of the two diodes are connected to the ends of the secondary of the transformer. The end side of the diodes are connected together and the output is taken between the common point of the diodes and the midpoint of the secondary of the transformer. So for a full wave rectifier, the secondary of the transformer is provided with a center tapping and so it is called as the center tap transformer. As can be seen from the figure 14.1 and C, the voltage rectified by each diode is only half of the total secondary voltage. Each diode rectifies only for the half the cycle, but the two do so or for the alternate cycle. Thus, the output voltage, their common terminals, and the center tap for the transformer becomes a full wave rectified output. Note that there is another circuit of the full wave rectifier which does not need a center tap transformer but needs 4 diodes. Since the input voltage to a with respect to the center tap at an instant is positive, it is clear that at an instant voltage at B being out of the phase will be negative H1. So the diode D1 gets forward bias and the conducts while D2 gets the reverse bias or is not connecting. Hence, during the positive half cycle we get an output current and the output voltage across the load is to the RA as shown in the figure 14.9c. In the course of the AC cycle, when the voltage A at A becomes negative with respect to the center tap, the voltage at B would be positive. In this part of the cycle, diode D1 would not conduct, but diode D2 would give an output current and output voltage RL during the negative half cycle of the input AC. Thus, we get the output voltage during the both positive as well as the negative half of the cycle. Obviously, this is a more efficient circuit for getting the rectified voltage or the current than the half wave rectifier. फिर आता है the rectified voltage is in the form of the pulse of the shape of a half sinusoids, though it is unidirectionally does not have a steady value. To get a steady DC output from the pulsating voltage, normally a capacitor is connected across the output terminals parallel to the load RL. One can also use an inductor in series with RL for the same purpose, since the additional purpose circuit appear to filter out the AC ripple and give a pure DC voltage, so they are called the filters. Now we will discuss the role of the capacitor in filtering. When the voltage across the capacitor is rising, it gets charged. If there is no external load, it remains charged to the peak voltage of the rectified output. When there is load, it gets discharged through the load and the voltage across it begins to fall. If the next half cycle of the rectified output, it again gets charged to the peak value. The rate of the fall of the voltage across the capacitor depends immensely upon the product of the capacitance C and the effective RL within the circuit and is called as the time constant. To make the time constant large, value of the C should be large. So capacitor input filter is large capacitor. The output voltage obtained by using the capacitor input filter is near to the peak voltage of the rectified voltage. This type of the filter is most widely used in the power supplies. और फिर यहाँ पर दिखाए हुए कुछ जैसे ट्रांसफार्मर हो गया प्राइमरी और सेकेंडरी. हाफ वेव रेक्टिफायर सर्किट इनपुट एसी वोल्टेज एंड द आउटपुट वोल्टेज वेवफॉर्म्स एंड द रेक्टिफायर सर्किट दिखा हुआ इनपुट एसी हो गया, ये आउटपुट वोल्टेज दिखाया हुआ है. फिर आता है कि a full wave rectifier circuit input waveforms given to the diode D1 at A to the diode D2 at B. Output waveform across the load RL connected in the full wave rectifier circuit है, ये दिखाया हुआ है. तो यहाँ पर सेंटर टैप ट्रांसफार्मर डायोड D1, यहाँ पर डायोड D2, फिर आउटपुट दिखाया हुआ है ड्यू टू द D1, ड्यू टू D2, ड्यू टू D1 और ये हो गया ड्यू टू D2. फिर यहाँ पर दिखाया हुआ है ए फुल वेव रेक्टिफायर विद द कैपेसिटर फिल्टर इनपुट एंड द आउटपुट वोल्टेज ऑफ द रेक्टिफायर. यहाँ से पूछा भी है, ठीक है, ये है जो पूछा गया है. तो यहाँ पर दिखाया हुआ फुल वेव रेक्टिफायर डीसी कंपोनेंट हो गया, ये एफी इनपुट हो गया और ये आउटपुट विद द कैपेसिटर इनपुट फिल्टर है जो हो गया. फिर आता है समरी इसका है कि सेमीकंडक्टर are the basic materials used in the present solid-state electronic devices like the diode, transistor, IC, etc. Lattice structure and the atomic structure of the constituent elements decide whether the particular material will be the insulator, metal or semiconductor. Metals of the low resistivity 10 के -2 10 ohm meter. Insulators have very high resistivity greater than 10 8 ohm meter, while the semiconductors have intermediate values of the resistivity. Semiconductor are elemental, silicon, germanium, as well as the compounds GAF, FDF, etc. Pure semiconductor is called intrinsic semiconductor, and the presence of the charge carriers, electrons, and the holes is an intrinsic comparative property of the material, and these are obtained as the result of the thermal excitation. The number of the electrons is equal to the number of the holes in the intrinsic conductor. Holes are essentially electrons vacancy with an effective positive charge. The number of the charge carriers can be changed by doping of a suitable impurity of the in the pure semiconductor, but such semiconductors are known as extrinsic semiconductors. There are two types of the N type and the P type. In the N type semiconductors, N is much greater than NH, while in the P type semiconductor, NH is much greater than NE. N-type semiconducting silicon or germanium obtained by doping with the pentavalent atoms like the arsenic spp, while p-type silicon or G can be obtained by doping with the trivalent atoms obtained like the B, L, N into C. Ne into NH equal to Ni square in all cases. Further, the material possesses an overall charge neutrality. There are two distinct bands of energy called the valence band and the conduction band in which the electrons in a material lie. Valence band energy are low as compared to the conduction band energy. All energy levels in the valence band are filled with energy, while energy levels in the conduction band may be fully empty or partially filled. The electrons in the conduction band are free to move in a fluid and are responsible for the conductivity. The extent of the conductivity depends upon the energy gap between the top of the valence band and the bottom of the conduction band. You see, the electrons valence bands can be excited by the heat, light, or the electrical energy to the conduction band, and thus the produce a change in the current flowing in the semiconductor. For insulator, Eg is greater than 3 electron volt. For semiconductor, Eg is to 0.2 electron volt to 3 electron volt, while for the metals, Eg is equal to 0. PN junction is the key to all the semiconductor devices. When such a junction is made, depletion layer is formed consisting of the immovable iron core devoid of their electrons or the holes. This is responsible for a junctional potential barrier. By changing the externally applied voltage, junction barriers can be changed in forward bias and side connected to the negative terminal of the battery and the P side connected to the positive. The barrier is decreased while the barrier increases in the reverse bias. Since the forward bias current is more milliampere by it is very small microampere in a PN junction diode. Diodes can be used for rectifying an AC voltage, restricting the AC voltage to one direction with the help of a capacitor of a suitable filter. A DC voltage can be obtained. अब यहाँ पर कुछ इंपॉर्टेंट पॉइंट्स हैं जैसे कि the energy band EC or EB in the semiconductor are space delocalized, which means that they are not located in a specific place inside the solid. The energy are the overall in average. When you see a picture in the which the EC or the EB are drawn as a straight line, then they should be respectively taken as the bottom or the conduction band energy levels on the top of the valence band energy level. In the elemental semiconductor, silicon or germanium, the N-type or the P-type semiconductors are obtained by introducing the dopant side effects. In a compound semiconductor, the change in the relative stoichiometry ratio can also change the type of the semiconductor. For example, in the ideal GAF, the ratio of the GAF is 1:1, but in the GA-rich or the AF-rich GAF, it could be respectively be GA 1.1 or AF 0.9 or GA 0.9 or AF 1.1. In general, the presence of the defect control the property of the semiconductor in many ways. अब इसका कुछ सॉल्यूशंस देख लेते हैं इसके क्वेश्चन का सॉल्यूशंस. तो इन द एन टाइप सेमीकॉन विच ऑफ द फॉलोइंग स्टेटमेंट इज ट्रू. तो इलेक्ट्रॉन्स आर मैग्नेटिक कैरियर्स एंड ट्रैवलेंट एटम्स इन द डोपेंट्स, तो ये है जो गलत स्टेटमेंट है. फिर इलेक्ट्रॉन्स आर मैग्नेटिक कैरियर्स एंड पेंटावैलेंट एटम्स ऑफ द डोपेंट्स, तो ये भी गलत हो जाएगा. होल्स आर द मैग्नेटिक कैरियर्स एंड पेंटावैलेंट एटम्स ऑफ द डोपेंट्स, तो ये सही है. होल्स आर द मैग्नेटिक कैरियर्स एंड ट्रैवलेंट एटम्स ऑफ द डोपेंट्स, तो ये हो जाएगा गलत हो जाएगा. In an N-type silicon, the electrons are the magnetic carrier, while the holes are the magnetic carriers. In an N-type semiconductor, is obtained when the pentavalent atoms such as the phosphorus are doped in the silicon atom. फिर आता है which of the following given in the 5.14.22 for the P-type semiconductor. तो in the P-type semiconductor, the holes are the magnetic carriers, while the electrons are the magnetic carriers. A P-type semiconductor is obtained when the trivalent atoms such as the aluminum are doped in the silicon atoms. फिर next question है कि silicon, carbon, silicon and germanium have 4 valence electron each. These are characterized by the valence and the conduction band separated by the energy band gap respectively equal to EGC, EGFI and the EGFE. तो which of the following statement is true? The answer होगा ऑप्शन सी कि EGC, EGFI and the कार्बन का, फिर उसके बाद सिलिकॉन का और फिर आ जाएगा जर्मेनियम का. तो करेक्ट आंसर कौन जाएगा? ऑप्शन सी. ऑफ द 3 गिवन एलिमेंट्स द एनर्जी बैंड गैप ऑफ द कार्बन इज द मैक्सिमम एंड दैट ऑफ द जर्मेनियम है जो कम हो जाएगा. तो द एनर्जी बैंड गैप ऑफ द एलिमेंट्स रिलेटेड है सबसे ज़्यादा कार्बन का, फिर सिलिकॉन का, फिर हो जाएगा जर्मेनियम का. अगला क्वेश्चन है कि इन द अनबायोस्ड पी एन जंक्शन द होल्स डिफ्यूज फ्रॉम द पी रीजन टू द एन रीजन बिकॉज. आंसर होगा सी कि द होल कंसंट्रेशन इन द पी रीजन इज मोर एज कम्पेयर टू द एन रीजन. The diffusion of the charge carrier of the junction takes place from the region of the higher concentration to the region of the lower concentration. In this case, the p junction has a greater concentration of the hole than the n region. Hence, in an unbiased p junction, the hole diffuses from the p region to the n region. फिर आता है कि when a forward bias is applied to the p junction, तो it क्या होगा, तो it lowers the potential barrier. When a forward bias is applied to the p junction, it lowers the value of the potential barrier. In the case of the forward bias, the potential barrier opposes the applied voltage. Hence, the potential barrier crosses the पोटेंशियल जंक्शन गेट क्या हो जाएगा, रिड्यूस हो जाएगा. अगला क्वेश्चन है कि इफ द हाफ इन द हाफ पे रेक्टिफिकेशन व्हाट इज द आउटपुट फ्रीक्वेंसी इफ द इनपुट फ्रीक्वेंसी 50 हर्ट्ज, व्हाट इज द आउटपुट फ्रीक्वेंसी ऑफ ए फुल वेव रेक्टिफायर फॉर द सेम इनपुट फ्रीक्वेंसी. तो इनपुट फ्रीक्वेंसी हो जाएगा 50 हर्ट्ज फॉर ए हाफ वेव रेक्टिफायर. द आउटपुट फ्रीक्वेंसी इक्वल टू द इनपुट फ्रीक्वेंसी. तो आउटपुट फ्रीक्वेंसी हो गया 50 हर्ट्ज. फॉर फुल वेव रेक्टिफायर द आउटपुट फ्रीक्वेंसी ट्वाइस द इनपुट फ्रीक्वेंसी. तो आउटपुट फ्रीक्वेंसी हो जाएगा 2 गुना 50 यानी कि 100 हर्ट्ज हो जाएगा फुल वेव रेक्टिफायर में. हाफ रेक्टिफायर में तो इतना रहेगा, फुल में जो होता है ट्वाइस द इनपुट फ्रीक्वेंसी हो जाता है. तो यहाँ पर हो जाता है सेमीकंडक्टर और डिवाइसेज.